Okay, let's get started. It's 5 minutes past the hour, and I think we have, 35 people signed in. That's great. Thank you for attending this tutorial. This tutorial is about using Bluespec, which comes in two varieties, a Haskell variety and a system Verilog variety, for using it for designing hardware systems. And let me get through a few logistics first. And actually, I'm going to almost immediately now switch to sharing my screen. And I'm going to be switching back and forth between three windows as I look up on the screen. You can actually do this locally on your computer as well, which I'll explain as soon as we get to the shared screen. There'll be a web browser in which there's a main document, which is the tutorial document itself. There's a terminal window, which we'll just use for directory listings and makes and builds and runs and so on. And there'll be an Emacs window where we'll be looking at some code. Okay, so I'm going to get started on the sharing of my screen right now, which means my video will probably go off. What I would like to do is, after I do that, is if I could get some sense of whether it's legible. I've set the font sizes, etc., appropriately so that I think it should be visible to you, but it'll be good if I could get some positive feedback about that. So here we go, share screen. Okay, I'm sharing my screen. I wonder if somebody could just speak up and tell me, can you read what's on the screen, the web, in the middle of the screen, the web browser?
Looks good to me.
Okay,
yeah.
And then here on the left, I'm showing you an Emacs window. Can you read that?
Perfectly.
Yeah, too.
And here on the right is a terminal window. Can you read that?
Yes.
Or should I increase the font?
That was quite legible.
Yeah, they looks good.
Okay. Okay, great. So, so let's get started then. This is the tutorial materials are at this URL that you see highlighted on the screen here on GitHub. And this document is in that repository, and it's called ICFP 2020 Bluespec tutorial out there. Now, just a word about the document itself. There are two versions you'll see there. One is an ADoc and one is a HTML document. And you can, if your browser, so first thing is, if you're viewing it on GitHub, if you just click on that, it will automatically render it and show it as a web page for you. And if your browser has such a plugin, you can do it also locally in a browser. But if you don't have an ASCII doc conversion automatically happening like that, you can just take the HTML and show that on your browser. So that's what this document is. And it's just one huge document. And you can follow along on this. This document also, I have found that it renders for some reason, it renders maybe because of style sheets or something in different ways, depending on what platform you're on. So what I'm showing you here is the HTML version running locally on a Chromium browser on my computer. But if I show you this version, this is directly showing it off of GitHub. Which stylistically is a little different. It doesn't have the left side table of contents. It has a table of contents up front. And then internally, the styles are a little different. Doesn't matter which one. You're welcome to watch it in either way you like. So that's about the document. So through this 3 hours, I'm going to go through this document. We're going to go through a bunch of examples. I'm going to show you how to build, run, et cetera, et cetera. Now, before the tutorial, for the last week or two, I've been sending out publicity in the form of tweets and things like that about pre-installing some things. If you want to run it now during the tutorial while we are going through it. But if you're not doing that, that's fine too. You can just sit back and listen and watch. Everything that I'm doing has been described in this document, so you can do it later. So very briefly, this is what's involved. The central tool of interest is this thing called the BSC compiler. And this is the thing that has recently, by which I mean in January 2020, been made free and open source. The source code of the compiler, everything is open source and free on GitHub at the web link that you see out here. Prior to this, now the compiler itself is not a new artifact. It's been in development for, I would say, something like almost 20 years now, starting with some research work at MIT and then spinning out into a company called Sandburst and then spinning out in another company called Bluespec. It was offered as a product to commercial customers since 2005, but it has always been free for academia, etc. But now it's been made completely free and open source, even to industrial customers. So it's on GitHub. It has an Apache license, so it's a very permissive license, etc. So that's the main tool we're going to be using today, and actually that's enough if, to run everything. Since we're designing hardware, the question is how do you test it or how do you execute it? And we're going to be sticking to simulation today. And with BSC, there's a option when you generate code to create a standalone simulation. So that's all you need. However, if you're taking it further into an FPGA or an ASIC, of course, you'll be going via Verilog. So there's an option in the BSC compiler to generate Verilog, and then the Verilog goes through standard tools. Once you produce Verilog, you can, of course, run it in a Verilog simulator. And the next points here are the two recommendations I have. The simplest one to use is this one. It's free, it's open source, it's iVerilog. And on most package managers, like in Linux, if you say apt-get install iVerilog, you'll get it. There is also a simulator called Verilator from the link shown here called Veripool, which is much, much faster. So the simulator produced by BSC and Verilator are extremely fast. iVerilog is 10 to 20 times slower. So running an iVerilog is okay for small examples, but if you want larger examples, it's better to use either BlueSim or Verilator. Other tools mentioned here, there's a tool called GTK Wave. So when you are doing hardware, you typically produce waveforms as if you have an oscilloscope stuck into the hardware, and GTK Wave is something to display that. We'll see that as we go along in the tutorial. And as described earlier, all the materials are at this website. Now, we're going to go through 3 examples, as you might see on the table of contents here. There's one example here, which is kind of a very small hello world example where we're going to start, which is just to get you sort of familiarized with a few things. Then we're going to use bubble sort, which is, of course, not a good sorting algorithm, but it's good for pedagogy. But we're going to bring in concepts of concurrency and concurrent hardware and clocks and things like that when we get to bubble sort. And then what we're going to do is we are going to go to a much more serious design, which is basically a memory-to-memory sorting artifact, a piece of hardware that you tell it that here's an array in memory, here's some workspace in memory, please sort it for me and use the merge sort algorithm while you do it. So that's the hardware artifact we're going to be looking at today. And how are we going to run it? Well, what we're going to do is we're going to connect it into a complete SoC or system on a chip, which we call WinSoC. And it's going to be running, and that contains a RISC-V CPU called Flute. All of this is written in Bluespec. And they're all available at this GitHub website, so you can get it from there. In terms of platforms, all our development and all that is usually done on done on Linux basically. Ubuntu and Debian are the defaults, but lots of people run all this on Macs as well. I'm personally not very familiar with running on Macs, so I don't know what the issues are, but I think you can all of these tools can be installed and run on Macs as well. Okay. So I think, so let's jump into the material then. we have 3.5 hours, I believe, up till it's 2 o'clock, just past 2 o'clock Eastern time right now. We have up to 5:30. We'll stop maybe once or twice along the way for maybe a short 1 or 2 minute, maybe a 5-minute break every now and then. But otherwise, we will carry on. So before I start, does anybody want to say anything or ask any question or anything?
Yeah, I have a question. Would it
Yes.
be possible to maybe use the text chat for communication as well?
Sorry, could you speak a little louder?
Well, that's exactly the problem. I don't want to speak louder. That's why I'm asking if we could use the text chat.
Yes, on the Clouder web page, which I think you must be logged into, there is a chat on the bottom right under chat tutorials too. Is that the chat you're referring to?
Yes.
Okay, yeah, sure. Please, you can also type in questions or anything there. Now, somebody is saying they can't read either of the windows. Is that still the case? I can try increasing this. When you say either, can you read the window that's currently on? Maybe you can type your answer, Mr. Gergo Erdl or Erdi, if you could just type your answer. Can you read what's on the screen right now? I'm not sure he's here. He or she is hearing me. Not the black bulk text. By which you mean the windows on the left and right, or what? These are they were occluded at the moment.
No, what I mean is that I can read the titles, the section titles, right? But the actual text is very small. So
okay. Maybe I'll shift to this version. How about this? Is this a clearer view of things? This is the table of contents. I can increase the size of this.
I mean, it's okay. I can follow.
Can you see? How about now?
I can read it on my own screen.
Yeah, I mean, that's the other thing. You could go directly to the website and fire up the same HTML locally and follow along there if you like. Okay, so let me move on. First question is, why are we here? And curiosity would be fine as an answer, but also the other thing is that as it's become more and more difficult to scale the speed of processors because of Moore's law, Dennard scaling, and reasons like that, it's becoming obvious that more and more functionality will need custom hardware for that. Because typically, when you implement some computation in hardware, as opposed to interpreting it as a machine language program, machine code program on a CPU, you're removing at least one layer of interpretation, which is the hardware execution of CPU instructions. But on top of that, you may also be making better use of parallelism, bandwidth to memories, because you have distributed memories and so on. So you can get sometimes many orders of magnitude speed up and energy efficiency, better energy efficiency by going to custom hardware. And you know, we've already seen that in lots of machines we've used over decades. Like, for example, virtual memory address translation is something that's done in hardware. It could be interpreted in software, but it would never be fast enough. Floating point units, graphics, video encoders, etc. Network offload engines for very fast communication, for very high bandwidth multi-point connections, and so on. Signal processing, and so on. But nowadays, of course, the buzzwords are neural nets for AI and computer vision, radar, LiDAR for self-driving cars, cryptography for security, and so on. So for all of these, you might want to create a piece of hardware that in which you run this computation, that you offload it off a primary CPU basically as an accelerator for that piece of the computation. You should do this with care, which is what this little section about why you shouldn't do it is there, which is to say that, of course, if you're doing ASIC designs, you're talking about months to years of development and millions of dollars, so it's very high cost. FPGA designs can be turned around in hours to months, but they won't be as fast or energy efficient as ASICs. But their tools are not easy to use. So that's another issue. And the other question you need to think about carefully is single purpose. In other words, often when you do something in hardware, typically you're customizing the hardware for some particular computation, and it's going to be sitting idle if you're not doing that computation on your system. So these are all trade-offs, and each individual situation will determine what's good for you. So this picture, if you're not familiar with hardware before, will give you a sense of classical, sort of typical hardware flows by which people go from a concept to a working piece of hardware that implements that concept. The middle row here is the classical thing that has been there for the last, let's say, 40 years or something like that. On the left, what you see, you code an algorithm using Verilog or VHDL or System Verilog nowadays, which are sort of standard hardware design languages or HDLs. And that Verilog, I'm just going to keep using Verilog, but it's a placeholder for all these three. That Verilog, it can be executed or implemented in various ways. So one way is you can directly run it on a Verilog simulator. So we'll be seeing some of that during this tutorial, and all the major hardware vendors, Cadence, Synopsys, Mentor, Xilinx, etc., will all provide simulators as well. That Verilog can then be taken on an FPGA flow through FPGA tools, which are typically vendor-specific nowadays. The first part of that flow is called synthesis, where the description that you've given in Verilog is mapped down into very low-level primitives, specifically things like and/or gates and registers and so on. And so you get a circuit which is basically a graph of gates and registers and so on. And then it goes through a process called place and route, which is the graph of gates has no geometry associated with it. That is, it's just an abstract graph. In place and route, you're nailing down where in the two-dimensional space of the silicon resources that you have, this particular gate will live, and how will you connect these gates all together. At the end of that, you get something called a bit file, which you can load onto an FPGA and run. I'll say a little bit more about that in just a moment. In ASIC tools, on the other hand, you're also going to synthesis and place and route, but rather than mapping it to a given set of gates, you're actually running it through what's called a foundry, which is a silicon factory that takes your description and produces a silicon chip for you. So these are called ASICs, for application-specific integrated circuits. Now, for our purposes, the most easiest way to get into hardware design and execution is through the FPGA route. So let me say a little bit about what is an FPGA, in case I'm sure you've heard the term, but you may or may not know what it means. Here's a sort of abstract view of what is an FPGA. Just imagine that I had a piece of silicon that was organized into sort of Manhattan city blocks. And in each city block, I placed preloaded and a bunch of gates, AND gates, OR gates, and so on. And then on the streets and avenues, I preloaded a bunch of wires, which are shown by these lines out here. And just imagine that you have some way to connect a gate to a nearby wire on the street outside. Now, if you look at these red dots, and just think of those as places where I have decided that I am going to connect those intersecting lines. So this horizontal line connects to this vertical line connects to the horizontal line, and so on up to here. Effectively, what I've done is I've created a circuit from the output of this OR gate here all the way up to the input of that AND gate out here. So by choosing where I put these red dots onto a sea of gates, which are laid out on these Manhattan city blocks, you can effectively get a circuit to match whatever circuit topology you want out of here. And this is basically what FPGA tools do, which is they are essentially producing from your RTL. I mean, the synthesis is producing gates, and then the place and route is deciding which gates shall we use in these Manhattan city blocks, and how shall we connect them. And so if you think of any given circuit, it's characterized by the set of red dots I give you. Which are the wires that I actually connect? And so that thing can be expressed as a long vector of bits, and that's called a bit file. And to go back to this picture, that's what this bit file is. You load that bit file into FPGA, and it becomes the circuit that you want. So that's just by way of a little bit of background about what our targets are in this. Now, FPGAs are very easily available. They're available from many vendors. They go from a few tens of dollars to many thousands of dollars, depending on size and speed and things like that. And you can get boards in which, off-the-shelf boards that will just plug into a PCI bus into your computer, for example, or plug into a USB socket on your laptop, by which you can talk to the FPGA board and so on. Most of the tools here are unfortunately still very vendor specific, but there's one company which is highlighted here, which I would recommend taking a look at, called Symbiotic EDA, which is trying to deliver some open source, free and open source tools for FPGAs. They also do formal verification and stuff. In fact, formal verification is their main shtick, but they also do these free and open source things. Okay, so the plan on this tutorial is the following. Like I said, we're going to go through 3 examples, starting with a very simple hello world example. And like all hello world examples, the purpose is to get you familiarized with the tools and what the process is and what your output is going to look like and so on. Then we look at a bubble sort example, which is not a good sorting algorithm, but basically I would like to introduce parallelism and concurrency. Now, normally when we do a bubble sort in a traditional programming language, it's a sequential program, a doubly nested loop that does many passes through an array, swapping elements, etc. We'll actually do a first version that is exactly that, and then we'll change it so that it becomes concurrent to bubble sort algorithm. And finally, like I said, we'll do a much more serious sorting piece of hardware, which is from memory to memory. So in other words, I don't have all my data available all at once. I have to go through reads and writes through a memory interface in order to get to my data. And we'll connect it inside this a system on a chip, an SoC, which is running a RISC-V CPU. And what we'll do is we'll run a C program on the chip twice. Once, both of them doing merge sort. One of them will be just merge sort written in C and compiled for the CPU. So it's essentially running as software on the CPU. And the second time, all it will do is it will set the accelerator to do the same sort, and we can compare how fast it goes. Okay, now to talk about the BSC tool itself. This was open sourced on January 2020. And for various historical reasons, it turns out that we have 2 front ends on this tool. One which uses Haskell syntax, and one which uses a very system Verilog-ish in flavor. It's not system Verilog, but it uses kind of syntactic cues from system Verilog. There's a long story over a beer about why we have these 2 front ends. But in any case, it turns out both of these are equivalent and functional and interoperable. And in this tutorial, because I'm assuming all of you folks know Haskell, we're going to stay with the Haskell syntax, and we're not going to spend any time really on syntax and types and so on. We'll just take all that from Haskell knowledge. Okay, so let's start with our little hello world example. And actually, let's take a look at some of these directories. So going to this, let me increase this even more. So I'm in a clone of this thing, which is basically the repository I've been pointing you at. The documents you see are, at the top, the ADOC and the HTML version. And there's a directory called examples. And if you look at the examples, what you'll see is we have sort of 3 versions of Hello World, 5 versions of bubble sort, and 1 version of merge sort. So we're not going to go through every single one of them, but that's the directory structure. And you'll see each of them has a source directory, which contains the source code for that example. And for each of them, what you'll find is in the top directory, there will be a make file by which we can make it. So let's take a look at the very first example, which is the O2A Hello World example. And I've just reproduced the code here in the document itself. And let's see what it means. So this is basically Haskell syntax, but the thing that you're going to keep coming back to over and over again here is it's Haskell syntax. In fact, exactly Haskell syntax and exactly the Haskell type system, but it's not Haskell at all. What we are producing out of this code is totally different from what one normally thinks of in one's head as how one executes a program. So we start with type declaration here, and we're defining a type for that variable, and the type constructor is module, and its parameter is empty. So module is kind of a central type here, and it is a monadic type in Haskell and represents an object, so a particular object. And the parameter type empty here is going to be describe the interface to that object. So in Bluespec, what you will see is that modules, to a certain extent, look like objects in an object-oriented language. That is, all interaction with a module is through method invocations on that on the interface of that object. And so empty is just a predefined interface which has no methods in it. So it's an empty interface. We'll see more interesting interfaces shortly. And then we're defining the value binding for that variable. And module is similar to, in a sense, to the do keyword in Haskell. It introduces a monadic sequence of statements. In our case, that happens to be just one of them, which is this one. And within the rules expression, it's defining a single thing, which we call a rule. And the rule has a name, which is just maybe used for debugging or something, otherwise has no semantic significance. And the key thing you'll find in a rule is certain keywords. When, do is just your standard do. This expression is called the condition on the rule. It says this rule is only allowed to execute when this condition is true. And then the body of the rule, which follows the this arrow, is itself a monadic expression. And in this case, there are 3 actions performed inside this rule. Now, $display is just like printf in C, or print line in Haskell. It just prints out something here, and it's kind of like printf. You can do formatted things, as you can see in the second $display here. It's going to print out these 2 arguments with given formattings over here. And finish is something that just says stop the simulation. So every time we look at a Bluespec program, you should have a mental model of what hardware we are describing, because that is what we're describing. We're not describing data structures or runtime structures on heaps and stacks and so on. We're describing directly hardware. And here's a picture that visualizes what that program does, right? So these blue boxes, think of these as module instances. And what I'm showing you here is a module hierarchy. There, you think of them as nested boxes, if you like, or a tree of boxes, if you want to look at it that way. With the outermost one being make top, and 3 internal boxes, which in this case, we're just going to imagine we have them just to get the intuition right. So just imagine somebody has given you a module which we're called $display deep thought says something, and it has a button on it, and when you press the button, the message lights up. Just imagine that. So there are 3 such boxes, and then here, this yellow box with rounded corners is going to be our rule. I'll write a condition above this line. In this case, it's trivially true, and the body underneath this line. And you can just think of this body as going and pushing those 3 buttons on those 3 boxes. So now, as I describe hardware, I'm going to repeatedly show you 2 levels of abstraction. This is a level of abstraction that is almost just a pictorial view of the Bluespec code itself. It's really not adding any information in your head, perhaps. But I'll also go a lower level to show you what it would look like had we really built hardware for this. That will include clocks and resets and various other kinds of signal wires and so on. A few comments about types here, which is that a rule in Bluespec is a first-class object. You can actually compute lists of rules, and you can generate rules and things like that. And its type is rule. Oops, I went the wrong way around on this. What did I do? I think I should not have worried about that. Okay, so it's of type rule. And a rule will have a condition. Its type will always be body, and the body type will, bool, and the body will always have type action. Now, the action of a rule is a recursive composition of subactions and subactions and subactions. So in general, there will be a collection of primitive actions that collectively still have the type action. And that's what we have out here. We'll see more and more of these types as we go along. Okay. Now, what about behavior? So far, what I've shown you is just a structural picture of what this code is. And indeed, that is the case in Bluespec. The Haskell syntax we're using is a notation and a mechanism by which we describe structure. What is a module? What is inside that module? What is inside that module? What are the rules inside modules? Which rules call what methods in what modules, etc. It's just a structural picture of what's going on in the hardware. There is a separate question of, once I've described such a structure, what does it do? How does it behave over time? So we'll separate this concept all the time, structure versus behavior. Everything you're seeing about Haskell is about structure, and nothing about the Haskell is about behavior. And behavior is a separate sort of a dynamic semantics that we talk about, which is about how rules execute. So you can think of a rule like an infinite process. That is, it's always alive. It's a infinite loop, if you like, and it can execute whenever its bool condition is true. And its body is an action, and conceptually, when it fires, you're doing all those actions that are in the body of the rule at one instant. It's just an instant. This is, of course, an abstraction, but that's fine. As an abstraction, it's just an instantaneous thing that happens. So let's try running this just to see what happens. So I'm in this. Let me go down into examples, and what you'll see is there's a make file and a source directory, and there's a single file, and top.bs is what we just looked at on the picture as shown out here. So the first thing I'm going to do is I'm going to compile it using BSC. So actually, nope, I don't have that set up. Let me just set that up. Okay, so basically I have installed and built BSC. By the way, as a side comment, BSC, which when you clone and download and install it from GitHub, BSC itself is written in Haskell. So you have to have, in order to build BSC itself, you will need GHC, the Haskell compiler, and then you can build BSC. But then once you built it, it's a standalone thing. It doesn't need the Haskell compiler anymore after that. So now, I'm going to do something that for which I've created a make target. So let's see what compile does. It's invoking BSC, and it's invoking it on the file of interest, source top.bs, and it's invoking it, telling me which module in that file is the top level module. It's trivial in this case, there's only one module, but in general, files could have more than one module in there. The other thing that it's saying is the -sim flag is basically telling BSC, I would like BSC to itself create a simulation executable. I don't want to use Verilog simulation for this. The next thing it's doing is if you look at this line here, this is a path. It's telling BSC where it should go to look for all the source files that it might need. So it will always look in the current directory, but in addition, it's going to look in the source directory. It's going to look into a nearby directory called resources, where I have one file called utilities. And this thing says also go and look in the standard Bluespec libraries. And finally, the final point I want to make is the -u here is, I think, similar to a flag in GHC as well, which is I'm only giving it the top level file and the top level module. Later on, you'll see that it will import other modules which are in other files, etc. And -u just says, please recursively follow those import chains and compile and link everything that you need based on that. So I only need to tell you the top level module and file over here. Let's ignore all the other flags. Some of these flags are just saying, please keep intermediate files in some intermediate directory so that they don't clutter my local directory, etc. And if we look at what it did, it in fact created this directory on that line over there, and it's populated it with some intermediate files. Don't worry about those. So the next thing I'm going to do is to say make b link, which is going to link it. Again, it invokes PSC, and again there are some flags that says points what are the top level modules, etc. And when it's finished linking, what you will see is that it has created these two files. One of them is a standard ELF shared object file, and the other is just a small script that invokes it. They could be combined into a single file, but that's the executable. And now when I say bsim, it will simulate. It's invoking the executable that we just created. And here's the $display outputs that's coming out of this. So it's straightforward. It's just very simple command line invocations for BSC to get it all running. So this is what I've explained in all of these things. And now let's take a look at, let's go down a level to look a little more detail at hardware. So far, everything has been at the level of rules and things like that, which is a more abstract level. Here's a slightly more, I'll call it fanciful, because of course I didn't really make a piece of hardware like this, but representing the same piece of hardware. So each of those sub-modules, what you'll find in general in hardware is, we're working with clock digital logic, is first of all, there is a clock signal that every module takes. So that comes in as a CLK, and it's sort of fed into all the different modules out here. Typically, every module will also have a reset signal, and here it's the RSTN. The N just means, again, this is a convention that some people use, which is that any signal, you can choose your convention about whether it's active low or active high. That is a low voltage or a high voltage, and resets are often active low. So RSTN is indicating that it's an inverted signal. And that's also fed to all the modules. Finally, every module will have one of these enable signals. That is the button that I was alluding to earlier, that when you press the button, something happens. And we're going to drive them with a constant value, true, or in this case, 1, if you want the digital value of 1. And these two modules have little displays that will come on. And this one, when you press the button, somehow it stops the simulation. Very fanciful, but I want you to start thinking in terms of directly the hardware that is created from the code that we start with. In general, we're not thinking at this level of detail of signals and clocks and resets and so on. But like lots of like any programming language, once you start thinking about performance, and in hardware, that performance may be speed, it may be area, etc. You start developing a mental model of what the final output looks like and how to optimize it and things like that.
I have a question. So
okay, so one other point I should talk about, in case if you had no background in hardware at all, in clocked digital hardware, there is one signal called the clock, which is basically a square wave oscillator. Okay, it just continuously flips back and forth between a low voltage and a high voltage with a vertical edge from 0 to 1 and 1 to 0. And typically in digital hardware, any state changes, any action that happens exactly on a clock edge. So the overall behavior of hardware is that if you think that at a particular clock edge, all the state elements have certain values, then over the period of the clock, those values, the electrical voltages coming out of state elements propagate through gates and transistors and MOSFETs and things like that, and eventually reach the inputs of other state elements. And at the next clock edge, it gets captured by the next state element. So everything happens on a clock edge, and the gap between clocks is basically to give the physics. It's physics. It's giving you enough time for the signals physically to propagate across the wires from one state element to the next. Okay, so exactly the same program, we can also.
I have a question.
Yes, please go ahead.
So I have a question. So I tried, like, looking at this diagram, I tried changing the example program to change the order so that the finish close is before the two display closes. And based on the diagram, I was expecting the output to be the same. Whereas if I tried running it in the simulation, it doesn't print any of the two messages.
Okay, that's a good question. So let me first talk about the sort of general semantics, and then also about specifically what you might be seeing in what you tried. All the three primitives we're looking at here, the $displays and the $finishes, are just kind of simulation artifacts. In other words, in real hardware, unless you really give me a box that looks like these display and finish boxes, no such thing comes as a primitive in hardware. You can produce such a box, but typically hardware doesn't have that. So, but of course, we can easily do these things in simulators because we're just pretending that we're actually doing hardware. And similarly, in hardware, when you when you do it in the semantic view of actions in Bluespec, all the actions in a rule conceptually happen at exactly the same moment. And we will see that over and over again. Now, when you have this particular example program, because we're writing as text, this text happens to be written in some particular order. They're not, that's because we have to write the text. Text is linear, so we have to write it in some order. But it's not supposed to indicate any semantic ordering between these things. And conceptually, they happen at the same moment. And if we had some way of doing it, you know, these displays might pop up on 3 separate windows at exactly the same moment, you know, depending on how we implement the simulation of $display, etc. Now, it just so happens in BSC, what we do is when we see a bunch of displays and finishes, which are simulation artifacts in the text, we will produce simulation code that, because it's running on a sequential computer, happen to go in that order. So it's quite possible that if you move the finish earlier, that it will execute that earlier, and it might stop before it does the finish. But conceptually, they're all supposed to happen at exactly the same moment. Now, except for simulation artifacts, it doesn't matter what order, like these displays and so on. It really doesn't matter what order you write actions in. Okay, so let's do the Verilog of this. So if I do a make v compile, you'll see that I'm again invoking BSC, but instead of saying -sim, I've provided the -Verilog flag. And that is basically telling the compiler to please generate Verilog for me. And in fact, in this flag, we are telling it, giving it a directory name to say, please put the Verilog in that directory. So if you look at our directories here again, what you will see that it's now created this directory. And if we look at that, there is now a file called mctop.v. And if we look at that file, you will see Verilog code that has been generated by the Bluespec compiler. Again, in general, one doesn't spend any time reading Verilog code generated by BSV, but it's good to develop intuitions about what's going on under the covers. So once we've generated the Verilog, we can then simulate it. And what I'm going to do now is I'm going to if I do a make vlink, what it's doing is it's again invoking BSC, and with this flag here, it's telling BSC to please generate an executable for the iVerilog simulator. Now you can, instead of iVerilog, you could also give the simulator names for Cadence simulators, Mentor simulators, Synopsys simulators, and so on and so forth. Unfortunately, each of them has slightly different conventions on how the top level is wrapped, and if you import C code, how it's imported, and all that kind of stuff. So BSC sort of takes care of all those details for you in this link step. And once I have that link, I can then simulate it, and you'll see it produces the same output as before. Okay, so that's our very first program. We've seen how you express it in BH, in this case, or BSV. We run it through BSC either to produce a BlueSim, or we generate Verilog, and then we can either run BlueSim directly, or we can simulate a Verilog. And the Verilog can then, of course, could be taken further for other downstream Verilog tools. So let's step back for a moment and just reinforce that we're doing something, we're describing hardware here. It's not the usual mode of computation one might be used to in traditional programming languages. So if you just compare what we're doing, let's say we're writing and executing a Haskell program versus a Bluespec BH BSV program. On both of them, on the left, we are writing using the same syntax and a same type system, although a different set of preloaded types, primitive types. In Haskell, we run it through GHC. It produces some object code, and then we interpret that. When I say interpret, we execute it. And in GHC's case, it's generating machine code. So your interpreter is an actual x86 CPU or an ARM CPU or something like that. And you have a mental model of what it's doing. You typically don't think directly in terms of memory. You think in terms of stacks and heaps and objects on the heap and closures and things like that, evaluation strategies and so on. So that's your mental model of what is executing when you execute a Haskell program. In BSV or BH, on the other hand, when you do BSC, you're describing a hardware module hierarchy. And you can, at one level of abstraction, just think of that plus rules. And the dynamic model of computation is rules are executing in steps infinitely as long as their conditions are true. And every time they execute, some state change happens. And if we go to a little more detail into clocked hardware, it actually goes an extra step in BSC called scheduling, where it maps multiple rules into individual clocks. And then we have produce actual Verilog with signals and wires and so on. And the dynamic model, again, is very similar in the sense that you have state objects, clocks, and state transitions that happen on clocks. So this is the mental model. And the key point about why you need to think here instead of there is ultimately regarding performance, which is why we're getting into hardware design in the first place, which is that the cost of your program in terms of space and time depends on precisely these things: how this dynamic model works. What is the dynamic model? What is the cost of various operations, etc.? That is completely different and can be totally different in this world out here. And so certain intuitions that one might have developed over time as a habit in running software programming about loops and recursion and so on may not hold in this, because you have a completely different cost model, a potentially completely different cost model over here. So this is the biggest hurdle to get through in designing hardware. Actually, that is true whichever language you start with, whether it's Bluespec or Chisel or HLS or anything like that. But it's this model of what you are designing, the dynamic semantics that you always have at the back of your mind when you're writing any program.
Question.
Yes?
Can you give some example of like suppose that I use a single clock. Can you give some example of the differences between the BSC and the BSC scheduling model in that case? Because I assume that the rule-based state transition thing is still synchronous. So
Yeah, I'll have a lot more to say about this later. So in general, when we are producing Bluespec designs, we sort of shift between different levels of abstraction in the way we think about things. One is we just think in terms of rules, and for a lot of purposes, including most of the reasoning about functional correctness of a design, just thinking in terms of rules and rule firing, and just thinking in terms of abstract rule steps without worrying about what wall clock time a rule takes is enough for establishing things like functional correctness and so on. Of course, ultimately, you're interested in wall clock time of how fast your design runs. And then we start thinking a little more about how rules get mapped into clocks, how many rules fire on a clock, etc. So this latter question of exactly how we map into clocks and think in terms of real time, I'd like to defer for a little bit and first present these intuitions. Okay, so let's go to a second example, a version of this example, where we're, instead of talking about a single file, we're going to talk about two different files and packages and modules. And this is in the 002B directory. All right, so let me. And let me bring it up actually here. So I'm now going to have two modules, a top module like we had before, except now we'll have a sub module which is going to be called deep thought. And you'll see why it's called that in a moment. And the top module is going to ask deep thought, what is the answer? And deep thought will give it an answer. So here's the code on the left-hand side out here. And the first thing that you will see is there's a package declaration. We'll get to that in a second. But now we are going to define an interface. So in the previous example, we saw one predefined interface that we were using that was the empty interface. Here we have an interface that has one method called getAnswer, and this is its type. So action value is a monadic type. So again, think by analogy with the IO type, IO monadic type in Haskell. So what this is basically saying is that this method, when invoked, will perform an action just like the IO monad does, and then it will return a value of this type, which happens to be int32. So the first two separate things to think about there. One is there's an action value that does an action and returns a value. That's part of it. The other part of it is what is the type that it returns. In this case, it's an int32. So in BSV, you will see that we use these numeric types like 32 here to actually specify widths of certain things. So an int32 is exactly a 32-bit integer. And you can supply any numeric type parameter you like there. Like you can have an int17 if you want a 17-bit integer, for example. They don't have to be multiples of bytes or anything like that. You can pick whatever size you like for that. So numeric types are part of the type system in BSV and Bluespec, and they're strongly type checked. So they have to match exactly in order to get get type checking done correctly. Now here is the module called deep thought, and you'll see that instead of the empty interface, it has the interface type that we just defined. Therefore, it has this one interface method, and here in this interface expression, we specify the method we're defining, and the body of the method is the monadic return 42, which says it does a trivial or no action and returns the int32 whose value is 42. Now this annotation here is in a comment, and what it's doing is basically the following, which is that if you look at our pictures that I showed of the hardware earlier, this one, which is the Verilog view of the world, and this one, which is the sort of rule level view of the world, well, structurally, they're very similar. They have the same sort of module hierarchy, top level module, 3 modules inside it, etc. The Verilog one has a little more detail. And this is generally true in BSVs, which is that when you go from BSV all the way down to Verilog, there are no surprises in terms of the structure of what you're defining in the Verilog. It's very predictable from the source code. However, you don't have to preserve every BSV module boundary in the Verilog. And that is controlled by this annotation here, which says, if you have this annotation, it says, please preserve the hierarchy here. And if you don't have this annotation, it says, please just inline it. Wherever you instantiate this module, just take the body of this module and inline it over there instead. So that's all there is to that particular thing. I should just make a side comment, and there's more discussion in the text over here which you will see over here on the section called synthesis boundaries, which basically says that not all Verilog BSV module boundaries can be made into Verilog boundaries because BSV is more expressive than Verilog. In BSV, you can have arguments and results of higher order functions and things like that, which have no obvious direct and canonical representation in terms of bits as wires at the interface of a module. And those things can't be made themselves into Verilog modules, but they can be used in a program, and through inlining, etc., they will all disappear, and the remaining modules that you have should have a Verilog interpretation where we can just generate Verilog for those. So that's the deep thought module, and let's look at the top module here. First thing you'll see is that there is an import statement here called deep thought, and this is how this module imports what was specified in the other module. And then what we see here in the module, and as I said before, this module keyword is like do. It opens a monadic context, and in this monadic context, we instantiate deep thought, which returns its interface, and that's what we bind to the identify deep thought here. And in the rules, what you see here is we invoke the get answer method, which performs an action, in this case a trivial action that does nothing, but it also returns a value, which is 42, which gets bound to X. And then finally we display and finish as before. So what you've already seen are sort of the two most important monadic types that you will see throughout Bluespec programs. One is this module monad, which is introduced here by this module keyword, and here are the statements in that module monad. And the other is the action monad, which is introduced. You can either use do or you can say action, and these are the statements. One of these is static and one of these is dynamic. And what I mean by that is that the module monad is statically executed by the BSC compiler because it is describing the structure of the hardware you're doing. So it is executed in order to describe a hardware circuit. The action monad, on the other hand, is of course completely dynamic. This is saying what happens when the hardware actually executes. But if you keep those two things in mind, you're sort of 90% of the way in terms of understanding how to use Bluespec. One other small comment I want to make is that in Haskell, the top level thing here is called a module. So there's a little bit of a confusion here, which is here we call it a package. And by top level, what I mean is this is a namespace, right? It's in a separate file. It defines a bunch of identifiers in this file. And when you import a package, it brings in the identifiers that are defined in that package. And then there are ways by which you can say package.identifier to disambiguate if you import two packages that happen to define the same variable, etc. that functionality, that namespace control in Haskell is called module. Unfortunately, or fortunately, anyway, in the hardware world, module with 40 years of history represents these hardware artifacts, these hardware gadgets. And so we've stuck to using module for this purpose and instead using package, which is actually the system Verilog word for namespace control out here. Okay. So what do we now want to do? I think I've finished talking about all of these things. And let's just quickly make this. And what you will see here is that during the compilation, it compiles deepthought.bs, even though in my source language, source code, sorry, in the command line, I only specify top.bs. So this is the standard import chasing that's happening, and it does that. And so if I do this, and we basically get the answer. And let's just do the Verilog thing for just a moment, just to show you that so we've compiled, linked, and run it in Verilog simulation. But if we look at our Verilog RTL directory now, you will see that there are now two files, one for deepthought and one for make.top.v. So the top module will always have a .v file, and when you have this Verilog make.top Verilog directive to the compiler, it will also create a Verilog for that. And these are just completely standard Verilog, synthesizable Verilog. You can just run it through standard Verilog tools. Okay, so let's now take a so far, nothing interesting by way of time, right? There's a single rule. It fires once. It does a couple of displays and finishes in one shot. So now let's introduce a notion of time. It's still an abstract notion of time initially, where we're just going to talk in terms of steps. Just think of every rule as an instantaneous execution. And when it executes, it's governed by whether its condition is true or not. And if it fires, its body changes some state. At the end of that, perhaps its condition is still true, in which case it will fire again and again and again, and so on and so forth. So we're going to show a small version of this. So in this example, what we're going to do is we're going to change deepthought into a state machine, which takes some time. In top.bs, we're going to split it up into two rules. One rule is going to ask deepthought, what is the answer? And then later on, then deepthought will go into its state machine, and we're going to pretend that it thinks for 7.5 million years. And then top is going to call another method. Another rule in top is going to call a method says, tell me what the answer is, and I'll get the answer and print it out. So those of you who've read Hitchhiker's Guide to the Galaxy, I'm sure we'll get all the illusions, over there. Okay, so let's take a look at the new deepthought. So first of all, we now have two methods. One method is, what is the answer? That's the question that top will ask. And it's merely an action. It just kicks off the computation. It doesn't return any value. You can think of action as action value returning void, if you like. And get answer is just as before. Now, in the state machine, we're going to define a data type here, which has these three states in it. This is just an algebraic data type, just like you might see in Haskell. Idle, thinking, and answer ready. And we can derive certain type class methods automatically in Bluespec. EQ is the usual thing, that is, it derives the equality operator on these values. Bits is a standard type class which says, which has the methods pack and unpack, which convert any type that you want, that is in the bits class, into bit n. So some representation of some of in bits of with some with n. So in this particular case, what the compiler will do is it will generate pack and unpack to and from bits 2. It needs 2 bits to represent 3 values. So it will use 2 bits and it will code them as 0, 1, and 2 respectively in going from left to right on these things. The third deriving here, fshow, is similar to show in Haskell. In show in Haskell, you're deriving you're producing a string output when you apply the fshow, the show function. Here, fshow is a formatted show, so it's a little richer in the sense that you can there's a statement called $format that is just like $display, where you can give a formatted string and a couple of arguments and get it formatted, and it produces something of type FMT format, which you can use in $displays and so on. So it's a little more expressive than just using strings per se. Okay, so the next thing we're going to look at is we're now going to instantiate some real state elements, as opposed to the fake state elements I was showing earlier, like $display and so on. So here, again, we're in this module, we're now into a monadic context. And so this monadic assignment will tell you that this guy is going to be a module that gets instantiated. And it's going to, what it returns is the interface for that module. The interface has this type, namely a register whose contents are of type state dt. And we're binding that to this variable out here. This value here is an initialization value. It says when the register, at the start of time, what will be the value in the register? And this is just telling you what the initial value will be. Essentially, it uses the reset mechanism of clock logic to be able to create an initial value in the register. Registers are strongly typed. So the fact that I've specified this type says that this register can only hold values of that type. Similarly, here we have another register called register half millennia. We instantiate a register initialized to 0. It returns a register interface where the contents of the register are 4-bit values. I'm using a 4-bit value because I'm going to be able to count up to 15. These are half millennia, so that represents 7.5 million years, which is the count that we want. These two are just ordinary let bindings with arbitrary expressions on the right-hand side. In this case, the expressions are bit selection expressions. So this expression says, please select bits 1 through 3 of the 4-bit value that's in reg millennia. So this variable actually has, we could declare it explicitly with its type, but it's an inferred type will be bit 3. And similarly, here we are selecting the 0th bit of half millennia, and this one's inferred type will be bit 1. Okay, and now let's, before we look at the rules, let's start with this initial question that will be asked from outside. What is the answer? So now you see that the rule, this method, like the rules we saw earlier, has a condition on it. That is, this method is only eligible to execute when this condition is true. And since we've initialized the register as shown here to idle, this method will actually be enabled at the start of time. When this method is invoked, it performs one action, which is this one. It assigns the value thinking to the state register. Now, once we assign that value, you will see that this method is now no longer eligible to be invoked because this condition for the method is no longer true. However, what we will find is that this condition on the rule is now true because that Boolean value is now true. And so we will perform the action of this rule, which is all of these things. Well, what are these actions? Well, it writes this statement. There's another action that's conditional. Every half millennium, we'll also write 0.5 out. And then we write this. So what you're seeing here is you're seeing some $writes and some $displays. This is like print and println in Haskell. $rights do not append end of line, and $displays do append an end of line at the end of this. And then the final action here is also conditional, which says that if my half millennia is 15, that is, I've counted up 7.5 million years, then let's change the state to this. Otherwise, let's just increment half millennia. So now what will happen? You'll see that once we do the state change, this rule will no longer be eligible to fire. This method is still not eligible to fire, but this method is now eligible to fire because of its rule condition. And when it's invoked, what does it do? Well, it returns 42 as it did before, but it's also setting the state back to idle and half millennia back to zeros. In some sense, we're sort of cleaning up in case you want to ask the question again for a second round of the question. Of course, you'll still get the answer 42, but you don't have to do these state updates here, but I'm just cleaning it up out here. So that's basically what deep thought looks like. And if you look at top.bs, we import deep thought as before, we instantiate deep thought as before, and now we have two rules. We have this one and we have this one. This rule locally has a true condition. When it fires, it will print out this message and also invoke this method. What is the answer in deep thought? So just again, reassure yourself that the types are all okay. So what is the answer is a method whose type is action. So this expression has type action. $display has type action. And in this monadic do, we've taken two actions and we can compose a composite action out of that. Now, the interesting thing about this is that this rule, even though this condition is true, remember that we also need this condition to be true for a rule to fire. So a rule should fire when all the conditions that concern it are true. That may include both what we call its explicit condition, which is listed over here, and also what we call its implicit conditions, that is conditions on methods that it invokes. So as you can see at the start of time, because this method is ready and this is true, at the start of time, this rule can indeed fire and will fire. Then as we saw in the other module, that will kick off the 7.5 million year state machine, at the end of which the third method becomes true. Until that point, in this rule, this method is not eligible to fire. Even though this condition is true, this method can't fire because of this. But at the end of that 7.5 million years, this method becomes eligible to fire. At that point, this whole rule becomes eligible to fire, and we invoke it. It's an action value, so we do the monadic invocation, which performs the action and returns 42 bound to x, which we just print out here. So let's just run it.
Sorry, I have a question.
Yes.
So did I get that right, that the condition for a rule is going to be all the conditions of all the actions that it runs? So does that mean that if I had some other action inside the rule for print answer, if that other action would not have its condition met, then the get answer action wouldn't run either?
Yes, you're correct. So let me just rephrase the question, which is there is a collection of a rule implies a collection of conditions. Some of them look very obvious. They're manifest in the rule body itself, but the rule one of its actions may be invoking a method. Inside that method, there may be more actions, etc. So transitively, if you follow these method invocations, there's a collection of actions that may be spread out over multiple modules in the module hierarchy. And the semantics of rules is that all of those actions must be enabled. In other words, all those methods need to be true in addition to any explicit Boolean condition that you give here. And when the rule is fired, all of those actions happen. Not only the ones you see here, but the ones in the methods and the method calls and so on and so forth. So that's the high level and simple intuitive view of things. There is a slight nuance that I would like to add, which is that if you go into our deep thought, you will see here that there is a conditional action, which says only if this condition is true do I want to do this right. And only if this condition is false do I want to do this action, which in this case happens to be no action. But for example, it could have been a method call, etc. So the answer is the Bluespec is very careful about saying that, about evaluating these rule conditions so that it knows it's only looking at the conditions that it might actually invoke in a particular instant. And for all of those conditions must be true and all the actions are done. Okay, so yeah, so
there was a question in chat on what the colon equals means.
Let me get to that first. So first of all, I'll get to that in just a second. Okay. Here is a so here I've actually executed it, and here you see. Oh, I'm sorry, I'm not in the right directory. I didn't go for 7.5 million years. So now I'm compiling it and linking it. And so here you see the output from the first rule, asking the ultimate question of life. Here you see the output from the rule inside deep thought that is executing. And then here you see the output from the final rule in the output. So let's get to this question that was just asked, which is what exactly does this this colon equals? What does this increment reg half millionaire equals half millionaire plus 1 mean? Okay, so let's I have some notes on it here, which I will. Yeah. Okay, so when we instantiate a register like this. So a register is just a primitive module, but it's just another module. By the way, this is another small difference, which is there is nothing special about registers in BSV. Everything about how its semantics all works is the same as the general module semantics. They just happen to be preloaded primitives for us. And so like all modules, this is instantiating a module and it's returning an interface. What is that interface? So first of all, what is the type of McReg? McReg itself has a type like this. It takes T, which is the initialization value, and it has type module because it instantiates a module when you invoke it, and it returns an interface of this type, a register that will contain values of type T. And that interface has two methods which are described by these types, underscore read and underscore write. So underscore read takes a register and returns the value that is the current contents of the register. And underscore write takes a register and a value, and it performs an action. Namely, it stores that value into the register so that subsequent reads will then see those values. And so when we see a assignment like this, it's actually, if you follow the general module method invocation syntax, it's equivalent to actually writing this. But this is a little tedious to write, and people like to see this kind of assignment for at least little things like registers. For everything else, we use the standard module invocation syntax, but it's just syntactic sugar. What you see here is just syntactic sugar for that. Okay? Okay. I'm sorry, I'm not paying very careful attention to the chats, but so please feel free to say question on chat or something if I'm ignoring you for too long. Okay, so that's what that's about registers. I think one other point I want to make is that we've already seen a couple of different kinds of method types. By method type, what I mean is the output type of a method will typically be one. You can think of it as three categories of them. Action methods, the output value is action. Action value T performs something and returns a value of type T. And in fact, you can think of them as the same thing. Action is just something that returns a void or something of no interest. And you have a type that is a pure value, that is that does not involve action. This is exactly like when you in Haskell you might think of T versus IO of T. So if something's of type IO of T, you know it has an IO action inside it, and it can only be used in that monadic way. Whereas if something is of type T, you are guaranteed that it has no side effects inside it. It is a pure value. So for example, one place where we would of course take care of advantage of that is the fact that the condition types of rules and the condition types of methods are of type bool, which is basically a pure type, not involving action, and therefore we are guaranteed that condition evaluation of rules itself will never cause a side effect. They can always be done. You can do them repeatedly, you can do them any number of times, you can optimize them, etc. Okay, having got through that, let's see where we reached. I think I've explained all of these things. We've compiled and linked it. Let's just take a quick visualization of the hardware for this. This is the rule view of the world. Again, it's just a pictorial representation almost of the text. There are 4 submodules. These yellow things I draw at the module boundaries are methods, and the yellow things here are rules. I deliberately use the same color and roughly the same shape, this rounded rectangle thing, because I would like you to internalize that methods are just pieces of rules. Methods have conditions, methods have bodies, just like rules have conditions and rules have bodies. And the abstract rule in some sense is the transitive closure of all the methods that it might invoke, collecting all its conditions and all the bodies of everything that it does. And all of them, the conditions need to be true. And when you execute the rule, all the actions in that collective rule are all executed together. And here's a slightly more hardware level view of things, which is that just imagine that there is some logic for rule ask and rule print answer. From the method, what is the answer? There will be a ready signal coming out, which feeds the rule. And then here we will combine it with any other conditions needed for rule ask. And we will take a decision whether rule ask fires. If it does fire, this signal is asserted, and that signal pushes the enable button here and pushes the enable button here. Of course, this enable button internally will do more things. We'll see that in a second. Similarly here, the ready signal from get answer comes here. We combine it with any other rule conditions that the rule might need. We pull out a will fire, and we push all the enable buttons that we need to do. And further, this being an action value, it also has an output value coming out, which is just plumbed into the dollar display here.
Question?
Yes.
So in this previous example, when you have multiple rules that are enabled, what is the order in which the action is executed? Are they interleaved from different rules, or does it different rules?
Okay, so the question to repeat it for everyone's sake is, what if multiple rules are enabled? In this particular example, we are fortunate that only one rule at a time happens to be enabled because of the way the conditions are all set up. But in general, more than one rule might be enabled at the same time. Now, that is a fairly big topic because here is the basic thing. At a very abstract level, every rule by definition is treated as an atomic transaction. In other words, it performs all the actions conceptually at one instant. And when you have multiple rules firing, being atomic, you should think of it as being serializable. That is, you can either think of it as rule 1 before rule 2 or rule 2 before rule 1. It is never the case that any intermediate state due to actions in one rule are ever visible to another rule. So you always see a consistent view of all the state that you are looking. Any rule always sees a consistent state of all the values that it's looking at. And when it does its action, conceptually, they all happen at once. And any other rule will only see either the values, all the values before or all the values after. By definition, they're defined as atomic transactions. Now, that's the abstract rule view. And at this abstract level, you can think of them as one at a time if you like. So, you know, I do this rule, then I do that rule, etc. And in some sense, the atomicity question is finessed when you think of it that way, because you're just doing them one at a time. But we still haven't thought about anything about real time, so you can think of them going as infinitely fast if you want. Of course, when we are producing actual hardware, we are going into clocked digital hardware. Now, if we were to map a rule, only one rule into a clock, then it would be a correct execution according to the semantics, but it might run very slowly because you're only doing one way. So what we would like to do is to be able to pack in multiple rules into a clock. But now we have to be careful because we have to maintain atomicity, because that's the semantic definition of rules are. So we will see a little later, we'll go into this topic a little more, much more deeply actually towards the end of the tutorial. There's a very careful consideration given into how we pack rules into clocks so that we balance off the idea of performance. That is, we try to pack as many rules as we can into a clock for maximum performance, but at the same time, we do never compromise atomicity, so that any reasoning you did about correctness that depended on atomicity will work even in the clocked hardware. So let me just defer the details of that for later, to just say that at the rule level, just think of it as some internal ordering. Either rule 1 goes before rule 2 or rule goes before rule 1. In fact, in the very next example of bubble sort, we are already going to encounter this. So, so we'll get to it very quickly. So here's the rule level view of deep thought. Again, not very informative. It's just a pictorial representation of the code. And here's a little hardware view of deep thought, right? So first of all, over here you see the two registers, reg state dt and reg half millennia. If you look at the output of reg state dt, which is not indicated in this diagram, but it's coming out of the bottom of the register, what you see is that it goes through a comparison with thinking, and that becomes the condition for rule think. Similarly, it's compared with idle, and that becomes the condition for what is the answer. And that becomes the ready signal for what is the answer. Similarly, on this line, you see you compare with answer ready, and it become the ready signal for get answer. Okay. Now let's see what happens if, let's say, let's imagine that what is the answer? The external environment says, okay, this is ready, and I choose to invoke this method. So I press the enable button, I assert enable. What happens there? Well, the enable button here is coming into this box, which is basically saying two things. It's first of all pressing this enable, which says load a value into this register. And it is setting some control signals here, which chooses which of these values gets loaded into the register. In particular, it'll choose the idle, sorry, it'll choose the thinking value to be loaded into this register. So that's a little hardware intuition about what is going on over there. And then for the rule think, now this condition might be true, and rule think does not have any other rule conditions to limit it. So let's say we choose to fire it. So we have the will fire signal of the rule. What does it do? Well, it also feeds this box, which also loads reg state dt, but it will decide here whether thinking or answer ready should be loaded in. Why can we make that decision? Because if you look at this register, it's compared to the termination condition of the rule, and it also feeds this box. So this box between that and this can decide which of thinking and answer ready should be loaded into break state. So a multiplexer is just a hardware representation of an if then else. That's all. It's just selecting one of its inputs based on control signals here, and so on and so forth. I'm not going to go through every level detail. If you look at reg half millennia, what you see is here we select the millennia bits and we feed it into this box. We select the 0th bit. We check whether we are at a half millennium or not, and that, along with the rule think will fire, decides whether you fire the 0.5, whether you display the 0.5 or not. And then we've already gone through this condition out here, and so on and so forth. So basically what you can see is that all of the constructs that we have seen in the source code, we can think of it abstractly like this, but every one of them has a mapping into actual real hardware as shown in this picture. The next thing I'd like to show you is waveforms. So what I'm going to do here is there's another make target that I've set up for you called make bsim BCD. And when I run it, it's going to run the simulation again, but it's going to run it giving the Bluesim this -v flag, which tells it, please also dump waveforms for this file. And you'll see that it has dumped that here. And here what we have is a file. So this is a very completely standard format in the hardware community. And it's the sort of simulated equivalent of placing an oscilloscope on every wire inside the circuit and capturing the waveforms that you would see on the oscilloscope screen, the ups and downs, the zeros and ones, and so on and so forth. So this thing can be displayed. There is a GTK wave is the tool I mentioned earlier. And if you run that on dump.vcd, on the left, you will see here a module hierarchy. And if I open out the module hierarchy, you will see our deep thought sitting inside top, which is the only two modules we worked with. But these things like main and all that are boilerplates supplied by the simulator around the top level module that you give it. When you click on a module, you'll see the list of all the signals that are in that module. So for example, if I click on the clock and I say append, what you will see the clock. And let me just zoom it in. You'll see here's the clock. And if I click on reset and append, you will see that reset is asserted because n means inverted. So it's asserted low. So it's asserted initially, and then we leave it as it is. And then if we look at a rule, for example, like rule, in fact, let's take a look at half millennia, for example, a register, and we append that, you will see that it's at 0 and it's incrementing its values as you go through this. So what you get essentially is a display of all the waves of this. And in hardware being highly concurrent, this is a very useful tool because you can see all the things that happen at a given instant during the hardware execution. I'm not going to go through all of this manually here. I have a picture that is shown here, which basically shows what I showed you. It shows a few more waves, like this waveform here shows you what is the answer, which happens right at the beginning. And this waveform here shows you get answer and rule print answer, which happens right at the end over here. So I should say that some people use waveforms a lot, almost exclusively. Other people rely on dollar displays. I'm much more of a dollar display person, but whatever suits you is fine in terms of how you visualize what's happening in your program and how you debug it and so on. Two other small points. Everything I've done is just simulation. It's source code. I've created a Bluesim simulation. I'm running a simulator on it, or I'm generating Verilog. I'm running a Verilog simulator. If I took that Verilog and I ran it through Verilog tools into an FPGA or an ASIC, and I actually put an oscilloscope on the wires, would I see the same waves or not? And this is what the term that is often used in the hardware community is cycle accurate. Is it a cycle accurate simulation? do I see in simulation exactly what I would see in the real hardware? And in BH, BSV, at least semantically, there's absolutely no difference. You should see exactly the same thing in both in the hardware and in Verilog. And in this is a little different from just Verilog and BHT and system Verilog for the following reason, which is those languages, those traditional hardware design languages, actually were originally designed as purely simulation languages. When I say originally, system Verilog is more recent, but Verilog and BHDL go back to the 1980s. They were just designed as simulation languages, and they have a simulation semantics, and they're in simulation. You can play all kinds of games, and in fact, it's more expressive than actual hardware. What do I mean by more expressive? Well, in simulation, let's say your hardware clock has a 10 nanosecond cycle period clock. Well, in simulation, you can say, I'm going to pretend I'm running for 3 nanoseconds and see the value on a wire. In hardware, there's really no way to do all of those things. And when you write code, if you do not stick to the subset of the language that is called the synthesizable subset, you might find that what you see in simulation, you see in actual hardware is different. Usually means you've forgotten to stick to the synthesizable subset. There's no such gotchas in BH and BSV. It's basically, there's just one semantics, and you should see exactly the same waveform in either way. One other point I'd like to emphasize, which is obvious from the pictures that I've been showing you, is that there is no surprise in the schematics that I'm showing you relative to the source text that I'm showing you. What are the modules? What are modules inside modules? Who's connecting to what, etc. Broadly speaking, that organization is called the microarchitecture. And I'm showing you exactly the microarchitecture that I want. And there are no surprises at all. And in this sense, Bluespec and Chisel are just like Verilog, system Verilog, and BHTL. You are always thinking of microarchitectures explicitly. I contrast this with another method of hardware design that has become somewhat popular in the last 10 years or so, called HLS, for high-level synthesis. In HLS, when you write your design, it's written in C or C++. And you actually never think in terms of hardware microarchitecture. You directly think in terms of C and C++, and you actually execute them as C or C++ programs. And then you use a tool to generate hardware from that. Now, that sounds like a tough ask, but it is essentially a problem of automatic parallelization of a sequential language, which is a very old problem going back to vector computers from the 1950s and 60s. You're given a sequential program, it used to be Fortran, but now it's C and C++, let's say, and you have to produce a parallel implementation. It used to be vector instructions. In HLS, it's parallel hardware. And as is the experience in that field is basically, if you have programs that are highly loop-based on rectangular arrays with simple index expressions, then the compiler has a chance of producing reasonable parallel code out of it. But the high-level point I want to make is that it's the tool that produces the microarchitecture. And in general, the Verilog produced from HLS tools is quite unreadable and difficult to discern what's going on out there. In BSV and BH, as well as in Chisel, because microarchitecture is so transparent, even when you are executing Verilog code, it's very easy to just imagine that you're directly executing BSV code. We also do a lot of engineering work on preserving names of signals, etc. So even though you might be running on a Verilog simulator that knows nothing about Bluespec, BH, or BSV, it is still possible to think in BSV and BH terms while you're doing that. Okay, one more remark before we move on to the next example, which is that you've already seen these types like int32, bit4, and all that. And in hardware design, unlike in software design, we're used to thinking in terms of multiples of bytes. And we quite casually extend things up to 64 bytes without even thinking about it. And if you want to go higher than 64 bytes, you have to do something major. Before that, it could be kept in a register. After that, it has to be kept in memory. There's no such boundary like that in when you're designing hardware. You get to choose how wide a bit vector is, and whether it's a byte size or whether it's 23 bits, it doesn't matter. And for creating efficient hardware, we typically try to keep these sizes just large enough for purpose. We don't try to extend it up to 64 bytes or something like that. And so we're often skating closer to the edge with respect to things like overflows and wraparounds and so on. So you have to be a little careful on that. In BSV, these sizes are parts of the type system. So even though these things like 32 and 4 here look like integer literals, they're not integer values. They are integer types at one level up in the type hierarchy. And if you look at kinds, for those of you who are familiar with kinds, you'll see that ordinary types have this star kind, and numeric types have this hash kind out here. And everything is strongly type checked. There are also type classes on numeric types by which you can do arithmetic at the type level. So for example, if you want to write a polymorphic function that takes a j-bit vector and a k-bit vector and append them together to produce a j plus k-bit vector, you can express that in the type system and have it strongly type checked. Okay, I think we're done with this example. Let me just quickly look at my chat here to see if there's anything outstanding. I think there's one question about, does the write happen on the rising clock edge? Yes, in our compilation strategy, there's nothing in the BSV semantics says that that should happen, but in the BSV semantics, following sort of general tradition that everybody does, everything happens on so-called pos edges, which is the rising clock edges. There is another kind of question about controlling the prefix of signal names or names in the Verilog. That's also a good question, which is that, so here's the issue. I'm describing to you here programs in BSV, and I can live purely in the BSV world. I never have to even think about Verilog or look at the Verilog code. It's just, it's machine code, like machine code for Haskell. You don't have to look at it if you don't want to. And you can live entirely in that space. But however, just like in Haskell, you might have a foreign function interface by which Haskell needs to call a library that somebody else wrote in C. Similarly, you might, in BSV and BH, want to interact with some other piece of hardware that somebody else designed that was designed in Verilog or System Verilog or VHDL or something like that. So in BSV, there are all kinds of annotations you can provide on interfaces. So what I mean by that, in an interface like this one on the top left here, there are compile time annotations you can provide that first of all, that can control exactly what names are produced in the Verilog wires corresponding to a method on an interface, so that it will easily match with expected names from some Verilog context. The second thing is that in the hardware examples I've shown you, you've seen these extra control wires called enable going in to perform an action and a ready signal going out to indicate whether a method is true or not, right? So by default, you can think of every method as having conceptually, well, every method has a ready signal to say whether the method is ready or not. And any method that is an action or an action value needs an enable signal to say, when do you actually do it? Now, in many cases, you may not follow exactly that protocol about enabling, etc., and particularly when you're dealing with external things. So yes, there's deep things. I don't think we'll have time to go into all that detail. I'll just give you a pointer into this, namely that in our last example of merge sort, we are going to be connecting with an ARM AXI4 bus, which is defined by ARM using Verilog signal names, etc., and using a particular protocol for how modules interact with exchange data with each other. which is called the ARM AXI4 protocol. And you will actually find all of that code available in BSV and how we produce the ARM AXI code names, etc., in the later example that we see. Okay. And there's another question here about, are there specific types of hardware which are maybe more difficult to describe in Bluespec? I don't, not sure how to answer that question. First of all, Verilog and System Verilog and VHDL are very large languages that cover a fairly broad range of functionalities, including analog signals and so-called mixed signals and so on. So certainly BSV can do none of that. It's purely digital logic. From that point of view, there's no inherent reason why anything you could have said in classical digital logic in Verilog or VHDL that you couldn't also say it in BSV. As I had sort of alluded to earlier, by being able to control whether we have these enable signals and ready signals and all that, we can actually we can write BSV in a very Verilog-ish notation. It's kind of like you could write Haskell in a very assembly language style, and it would probably compile to just the assembly language you think of if you're being very careful about how you say that. Similarly, you can, it's very expressive. You could do, I think, anything you like. So I don't have any clear gotchas that you can't do in this. Okay, so I think we are now, we are almost 2 hours into our 3-hour tutorial, and I'm just past the first example. In any case, I need a 2-minute bio break. Perhaps you do too as well. So why don't we just put our pencils down for about 2 minutes, and we'll be back in about 2 minutes and resume. Okay? I'll be right back. Okay, I'm back. So before we move on, I would like to give a small shout out and an acknowledgement. I see in the chat that Leonard Augustin is with us, and he's a central player in this whole story. When Bluespec was started back in 2000-ish, Leonard was one of the first people in the company, and the first version of BSC that you're seeing here, used here, was designed, actually the first version of the language, Bluespec BH language, which you're seeing here, and its compiler BSC were designed and implemented by Leonard. So it's really a great testament to his to his design, as well as to the power of Haskell, etc., that it's 20 years old and it hasn't grown old. So that's great. Thank you, Leonard. Okay, I'm going to resume now, if that's okay with everyone. And given that it's going a little slower than I had expected it to go, I'm going to skip version A of this bubble sort example, which is basically a sequential thing, and go directly to version B, which is the concurrent version of things. So let's find that here. Okay, we're going to do a concurrent bubble sort, which is kind of an odd looking creature. Now, first of all, when we're talking about sorting, we're typically talking about an array or a list of something, right? So some collection of values. And when we're talking in a programming language, those are data structures that are sitting in memory. And we may think of an array or a list as a single object, but of course it's a data structure in memory. And under the covers, I mean, as part of the program execution, we're doing individual loads and stores of words from a memory to get the components of the array or list as we sort it. Well, so far I haven't said anything about memory. There is no memory object in anything I've described so far. So how do we manage a collection? Well, we'll get to that. We're going to manage collections with memory in the third example, but for the moment, we're just going to replicate a bunch of registers and say that we're going to sort arrays that will fit in these registers. And because this is just a tutorial in pedagogy, we'll just use 5 registers to start with. Okay, so the module will look like this, as shown in the picture. And what we're going to do is, next question is, how are we going to provide the sorter with the values to be sorted? What we're going to do is we're going to send them in serially, one after the other. And what we're going to do is, as each value comes in, we're going to put it into a register here. Now, for the moment, let's just assume that all the registers are initialized with some unusual value that we don't expect in input, an unusual huge value. We'll call that max bound, the max, some large plus infinity value. Let's assume that's there in all the registers. And then what we're going to do is, we're going to, between every pair of registers, we're going to have a rule that says that if my 2 registers, the ones I'm between, are not in the same order, we're just going to swap them. And that's it. That's what the rules are going to say. So what's going to happen is, when we provide the first value into this register here, the last register here, the rule sitting here that is looking at these 2 registers will see them out of order, because this is going to be the plus infinity value and this is going to be that initial value. So it'll swap them. So that first value will go there and plus infinity will come here. And then this rule can swap that. And then this rule can swap that one. And so what you see is that as soon as the first value is available, it can start bubbling up towards the left. And if we didn't give it any more values, it'll bubble all the way up to the left. When the next value comes in, similarly, it'll also start bubbling up. But if it ever encounters the first one and it's in the wrong order, then those will get swapped. So what I'm trying to paint a picture of is that all the swapping is happening willy-nilly in whatever order you like, doesn't matter, as values are streaming in on these unsorted inputs. So so that's basically the idea. And then what we're going to do is, when everything is sorted, which is we'll have a predicate that checks is everything sorted, we'll declare it done, at which point we'll stream outputs out from the register basically by shifting values out from this. So let's take a look at what that code looks like. We'll go to trio b bubble sort source bubble sort.bs. Okay, so first of all, let's take a look at the interface. Interface is two methods. The put method is this one by which we supply an int32 value and it does an action, namely it's going to put it in here. And the get interface is an action value that will retrieve an int32 out of this. And the action value will do the internal things of shifting and things like that. Okay. Here we will use this register in J to count values as they come in, so we know when we have got our full complement of values. In this case, let's say 5. And then here are our 5 registers, and they're all initialized to max bound. And max bound is actually the same as in Haskell for each. It's a type class. For every type there's a that is in the max bound class. There is a corresponding value that represents the largest value of that type, and we're going to use that. And it's going to the register is going to have int32. Now here's the predicate for deciding whether everything has been sorted or not, right? It's of type bool, and it's true when we have 5 values and x0 is less than x1, x1 is less than x2, x2 less than x3, and x3 less than x4, right? So that's just a comment, just a pure function, and pure functions just become combinational circuits. And then I'm going to, what you'll see in the source code is a bunch of these options. I'm going to skip those for now. It's a little more advanced, and go to the interface. So so here's the put interface. The put interface says x, you're allowed to accept a value x when you're still expecting values, and this last value x4 is max bound. Remember, when I do the first swap, when the first value actually, sorry, before I do the first swap, when the first value comes in, you know, I don't want to overwrite it with the next value. I want to first allow it to do the swap, bringing in the max bound here before the next value is allowed in. So that's why the condition is what it is. And when the condition is true, we take in the value into the last register x4, and we increment our counter. And as I described verbally earlier, once you do that, it's going to start swapping. As you keep putting in things, it's going to keep swapping stuff in here. And the get interface is predicated on the done predicate that we just looked at. And when it's done, what does it do? Well, it returns x0, that is the smallest value. And then here, it's shifting all the values up by one step, filling in max bound on the far right. And this condition just says that when I have shifted out the last value, at which point x1 will be max bound, I can just reset in so that I can get ready for my next invocation of sorting. Okay, so I hope the picture is clear about what's going on here, where it's basically a very concurrent bubble sort that is willy-nilly swapping values until everything settles down into an ordered thing. We don't have the sequential loop that we saw in what we typically see when we first see bubble sort, when we write it in a standard programming language. Okay, so let's take a look at some of the hardware that this represents. So the done predicate that we saw in the code, roughly speaking, looks like this. Here are the registers. We're checking that x0 is less than x1. This is checking x1 is less than x2, and so on. And we're ending all of those, and we're also checking that we have j is equal to 5. Now, for those of you who have ever sketched out a fold L or a fold R operation on the whiteboard, you might have drawn a picture just like this, with these being some maybe list elements or something like that. And in a later version of this, we are going to use exactly a fold L, and it's going to produce exactly this hardware. And so that's an example of what the done symbol is. What's a swap rule? Well, that's all there is to the swap rule if you see it in isolation, right? Because what this is saying is if these two values are not in the right order, then hit these enables, which will swap x1 and x2 on those two registers. Okay, so now we come across the question that was asked earlier. What if more than one rule? Well, certainly more than one rule could be enabled, but there's a bigger problem. There's a more serious issue here, which is when we have two, suppose we have look at these three registers, and suppose both of them want to swap at the same time. Both of them are reading and writing this shared register between those two rules. So what is the meaning of that? So here's where the atomicity comes in, which is at some level, at a certain abstraction level, we just finesse the question by saying, look, by definition, it's atomic. So I don't know, you pick an order, either do this rule before that or this rule before that, doesn't matter, but they should be done atomically. So so the fact that I'm reading and writing a value in both rules is never going to create a race condition that those reads and writes ever get interleaved because of atomicity. But in some sense, I've punted the problem, of course, to the implementation. The implementation has to figure out, how do I achieve this? And that's where the rule scheduling, et cetera, will come in. So although here I show you the swap in isolation, in fact, the swap will look a little more complicated like this. So first of all, the values that can come into a register are not only the value from the swap, this register, but if you were swapping x2 with x3, its value could come in here. So that's another input of the mux. And then at the start of time, of course, and in the methods, we are loading in max bound into the register. So that's another value here. So what you need is a multiplexer for all those possible values that can go into this x2, and some control logic here that selects the right thing from here. And it's this control logic and this similar control logic on the adjacent rule that between them will make sure that only if those two rules are both enabled at the same time, that they run in a suitable, in an order, so that they never step on each other's toes.
A question.
There is a question on chat about parameterization of modules. Yes, you can parameterize with anything you like. It's any type is okay. The only caveat is what I had mentioned earlier about is if you want to preserve a module boundary at a Verilog boundary, then there will be some restrictions on what kinds of parameters, etc., you can have. But as long as you're just expressing things as static elaboration, static structural elaboration conveniences, you can parameterize with any type you like. Okay. So what does the input look like for this circuit? Well, here, what you see is that from the X4 register, we are checking if that's equal to max bound. The RJ register, we're checking if that's less than 5. If those two are both true, the ready signal goes out. And then if the output chooses to do a put operation, it will assert n and provide x, and asserting n will hit this enable, which will increment j or store the increment of j, and this enable will capture x out here. And similarly for output, you can see what this looks like, which is that the ready signal is basically the done circuit that we looked at earlier. And if the output says enable, that is, please, I would like to get the value, then first of all, it will sample the value that comes out of here, which is the value that comes out of x0. But then through this enable, it will basically perform the shift that we described. By every enable, you can see enabling x2, for example, will store the value that used to be in x3. Enabling x3 stores the value that used to be in x4, and x4 gets and. So once again, just reinforcing the idea that everything we're describing has a hardware representation that is, as you start using this, you build your intuition about exactly what hardware you're getting from a BSV program. If we run this and look at the waveforms, which I've captured here already, Well, first of all, let's just run it once. File vlink vsim. Okay, first of all, you're seeing the inputs and outputs. I'm generating, these are the inputs. This is the rule coming from outside for the inputs. And this is the rule coming from the outside, which says here are the outputs that finally drain out. So this is the sort of unordered sequence, and here's the ordered sequence out here. During compilation, you will also see some warnings like this. And this is precisely the question we've been discussing about what happens if two rules may fire together, but they have some conflict on some shared state. Again, we'll talk about more detail about this, but these warnings concern exactly that question. And if you actually look at the waveforms, you will see that. So what I've selected here are the so-called will fire signals of the 4 rules in question. And you can see that on some clocks, like on this clock, this rule and that rule are firing. On this clock, this rule and that rule are firing. On this clock, this rule and this rule are firing, and so on. And so rules can, in fact, fire concurrently. And if I just scroll up a little earlier, you will see the waveforms from the sequential version of the bubble sort, which we did not go into for want of time, where you will see these rules run completely sequentially. In this case, 2 passes, and then it's sorted. And overall, you'll see that if you look at the time axis up here, it goes to 190 microseconds. What microseconds, you might ask? We'll discuss that in a moment, but it's 190, and here it's done it in a little shorter time, 130 microseconds. For both reasons, that it starts sorting as soon as it starts getting input, and it's exchanging things in parallel. Yeah, so don't take these 130 microseconds, 120 microseconds too seriously. This is simulation, so it's completely fake time. It's just that in Verilog simulation, you have to give it a clock, and you just declare that a clock takes so many microseconds or something, period, and it just shows you the thing as if that was the actual time. So in that sense, it's a bit of a fake time, but it's accurate in the sense of if you leave aside the time units that you're talking about and think about cycle 0, cycle 1, cycle 2, cycle 3, that is exactly what you should see in real hardware as well. Okay, so that's the bubble sort example, and I'd like to. There are 3 more versions. We're not going to go through those, especially in this Haskell audience, because it's just basically using Haskell expressivity to improve this program in various ways. Version C goes from 5 values to n values. Version D goes from sorting int 32s to any type T that is in the ORD class. And version E says instead of this fake max bound value, which may not even exist for some types, let's use a maybe type instead for and use just X if you actually have a value, and empty or nothing if you have no value. So that's all there is to it. And you'll see lots of details that those things imply. So for example, if you look at the interface of bubble sort, which previously was not a parameterized interface, it now has two parameters, a numeric type, which is how many things am I going to sort, and T, which is what is the type of things that I'm going to sort. And you can see from the kind signature here that this here is a numeric type, and this here is an ordinary type. And of course, the output type is an ordinary type. It's an action. Sorry, it's an interface type. If you look at the module itself, what you will see that it has now grown some type class constraints. That is, earlier you told me it was an int 32, so I knew I could make bits out of it. Now you're telling me it's type T. How do I know I can make bits out of it? By saying that T must be in the bits type class with a particular width WT, you're guaranteeing to me that it has a pack and unpack function, so I know how to store it in registers and take it out of registers and make wires out of it, etc. You're doing comparisons, so you must be in OR T so that I can do comparison. You're doing equality checks, so you must be in EQT so that I can do equality on it. And the module interface now has this parameterized type. You can move numeric types into the value space by applying value of. So when you apply value of to a numeric type, you get a numeric value that has that value of type integer. And then instead of laying out 5 registers explicitly like I did, what I'm going to do is I'm going to use a vector of n registers, and to each of which has a register interface, and the contents is going to be a maybe t. That is, it's either just x, in which is actually a value x, or it's nothing, in which case it means I don't have a value, I'm empty. And to create the vector, what do I do? Well, I take the individual register constructor, like mcreg invalid, and by using the monadic replicate n, I stamp out n registers and collect it in a vector called x's. Then for our true or done predicate, what we're going to do is essentially do a fold operation now, because we don't know how big n is, so we can't write it out explicitly. So here what we do is we generate a list from 0 to n minus 2, and then we use the all function, which is basically a fold on Boolean operators. And we have a lambda function that does the appropriate comparison on that. Then what you will see is that you can, rather than writing out those 4 rules explicitly, we write a function to generate the rule of interest, the swap rule. And then we use map over a list of that function, the function that we just defined, to produce a list of rules corresponding to the set of rules we want. And then we use this primitive called add rules to monadically add it to the collection of rules in the module. And the descending urgency is an additional specification which says, please add them in decreasing priority order as they show up in this list. So when you do that, in fact, these warnings will go away, because now you've told it what priority to execute rules in if they conflict on something. So I leave that up to you to read later on at your own leisure. But you can see how you can use essentially all the kinds of powerful things you can do in Haskell to express rules, to express collections of registers, to express circuits that are repetitive structures, all that kind of stuff. But all of this is about static elaboration, that is structure. All of these are expressive tools by which you can express complex structures. Once you've expressed a structure, the semantics of that is given by the semantics of rules. Okay, there is another question here, which is, are the order of executions the same? Is it dynamic? Is it deterministic, etc.? So once again, I should say that taken abstractly, the language places no position on whether rules are done in the same order on different clocks, on different orders, whether they're done deterministically, which one you choose if there's a conflict. Every one of these could be dynamic if you knew how to implement hardware for it, to implement that. The only sacrosanct thing is they have to be atomic. So anything you do that keeps it atomic is fine. And then you may add further constraints like that you must have a fair scheduling on these rules. You should never starve one rule if it's always conflicting with another rule that's always enabled, for example. Again, all of these are tactics on how you compile and strategies on how you compile. The base language semantics does not take any direct position on this. Now, the BSC compiler is very specific about what it does. That is, the choices it has made in that space of choices is very specific. It's, first of all, it's the same on every clock. So the ordering is static. So it's a static priority order. And And secondly, it's very conservative about how many things it can do on the clock and so on and so forth. So BSC, but you should try to separate out the concept of what the semantics could have allowed versus what BSC in today's implementation does. And so being an open source project, you might be inspired to do something better. So please contribute and improve the scheduler or provide alternative schedulers for what BSC can do. So there is another question here about, have you run into pathological cases where hardware complexity size explodes if you aren't careful in how you write a schedule of your rules? In general, the size question has not been problematic with respect to rules, and that may be because of the very narrow view we take of rules. That is, we make statically ordered deterministic schedules. Size is more likely on structure that you're not being very careful, because you can write recursive definitions, etc. here. And again, if you're not careful, it's doing static elaboration, so it might generate a huge circuit. I think with experience, you rarely encounter situations like that where things are surprising in terms of blowups. Okay. One small comment on style. You'll see that and this is my personal style. This is not recommended or anything like that. My personal style is recommended only by me, which is that I use certain stylistic conventions to talk about interfaces and registers and rules and value methods and action methods and action value methods and functions and so on and so forth. I'm not even very consistent on this. It's not a requirement, but in my opinion, it makes code readable. You kind of can instantly get a sense of what something is supposed to be doing if you use these hints like this. Okay. Next. There is another question about maybes. Okay, in Haskell, you have a maybe type, and its constructors are just and nothing. In hardware, the tradition is to have something called a valid bit accompanying data, which tells you whether the data is valid or not. So in BH and BSV, you'll often see instead valid and invalid as the constructors for these things. But I think you can use, I'm not quite sure, you might be able to use just and nothing as synonyms for that. Okay. Now, I think now we're ready to move into our third example, and just about time. Good, because this is in some sense starts getting interesting in terms of real-ish hardware. Okay, so we're going to start talking about accelerators now. And first of all, let's, for those who are not familiar with accelerators or just heard the term, etc., let's just say a few things about different kinds of accelerators. So what I'm showing you on this picture is a small SoC, system on a chip. System on a chip usually means a processor, which is this box on the top left. It might have caches and MMUs. There's typically a bus or a system interconnect, and that connects it to I/O devices and memory and so on. Accelerators come in many different flavors. And one dimension is how tightly coupled versus how loosely coupled they are with memory. So on the extremely tightly coupled end of the spectrum, it might be right inside the CPU pipeline itself, as for example, an alternative functional box. One example would be floating point, right? You have a floating point unit in your CPU. You don't have to. You can compile GCC code with the assumption that you don't have a floating point unit, and it will produce software that emulates IEEE floating point using integer instructions. But it's much slower if you do it that way. So having a floating point unit is nice, and it's typically very tightly integrated with the CPU pipeline. Another kind of accelerator might be a vector unit. shown in this box where my cursor is hovering at the moment. And that is typically not that tightly coupled. When I say not that tightly coupled, in floating point, for example, you might freely interleave floating point instructions and integer instructions. When you do vector things, you might have a vector instruction that kicks off a vector operation, and then sometime later you get the vector result. And in the meanwhile, you might be executing other integer instructions in the CPU pipeline. And so some of these might be called coprocessors, for example. And when you have these things, another question to be asked is, do they need to access memory, or are they only accessing CPU registers? If they access memory, do they go through the caches, and do they go through virtual memory translation, MMUs, or not? Or do they go directly to memory using, for example, physical addresses? All of these have their trade-offs, and I'm just listing out a bunch of things. And on the very far end of the spectrum, you might have something like this, which is going to be the subject of our example today, which is an accelerator that's just on the system interconnect, doesn't share anything with the CPU. Now, how does this accelerator run? Well, this is roughly the flow. What will happen is that in the CPU, we will do ordinary memory load and store instructions that will go through the memory hierarchy as usual, except because of their memory addresses, rather than coming to memory or to I/O devices, they will come into this box. And using this, we will inform this box about some information it needs for it to do its acceleration. For example, we're going to do sorting of two arrays. So we're going to give it the base pointer of the array to be sorted. And we're also going to give it a second temporary work array, which it can use as a scratch pad while it's doing the sorting. That will be of the same size as the array to be sorted itself. So we're going to give it two addresses of two arrays, A and B. Then we're going to tell it how many elements are there in that array. So that's a third parameter we give. So we'll do that through a series of 3 writes into the thing. So this is described by these 1, 2, 3, 4 bullet points here. But I'm explaining the same thing verbally here. So we do 3 writes, and then finally we will write one particular register here to say, okay, go. I've given you all the information you have. Please do your work. When that happens, this box will wake up to do its work, and what it will do is, through this interface, it will do all the reads and writes it needs in order to do the sorting. And when it's finally done, how do we know it's done? Well, what's going to happen is the CPU in our example here is going to poll for completion. And what that means is it will repeatedly read a register here, which will read as a 1 as long as the sort box is still busy. When it's completed, it will read as a 0. That will indicate to the CPU that the sorting is done. And then the CPU can proceed to use the sorted array after that. So that's the basic idea on this thing. It's okay if you're dealing with a lot of data and you don't need cache coherence and you don't need virtual memory translation, etc. All those other considerations might complicate the picture. Okay, so what are we going to do for our particular thing? Well, first thing I want to draw your attention to is this thing called the system interconnect. And system interconnects usually have 2 kinds of connections. And what I've shown them on the top side are things that I call initiators and clients. People also call them master interfaces. And on the bottom side, I'm calling them either targets or servers. That is, all the boxes over here are initiators and clients, and all the boxes here are targets or servers. The classical terminology for this is master and slave, which people find a little offensive. So we can't completely avoid it because we're going to be using some existing standard that uses that terminology. But think of these as just synonyms: initiators, clients, masters, and targets, servers, and slaves. Now, so what you see in the accelerator like this, it is both a target, which is how it gets configured. Oops, I did the wrong thing there. sorry. It's both a target on the interconnect, and it's also a initiator because it initiates reads and writes to memory. The specific interconnect we're going to use, type of interconnect we're going to use is defined by ARM, and it's called AXI4, AXI4. And there's a bibliography in this document that will tell you if you want to go look at it. It's an open standard by ARM, so anybody can implement AXI4 gadgets. And we're going to work with 64-bit words, and that's going to be it. So let's take a look at. We're going to look at the source code, and the source code is basically in this directory, e.g. 0040, 040 merge sort, and there's basically two files. One is something called a merge engine, and the other one is the outer level of the accelerator. The merge engine is kind of the internal engine used for merging, and this is the wrapper, which we'll look at in just a second. Okay, so let's just take a look at what we're trying to implement. This is pictorially what merge sort does. You have your input array of size n, and what we're going to do is we're going to think of something called a span, which is a contiguous set of a segment or with a given span. It's a contiguous segment of locations in the array, which we know to be sorted. And the base case will be spans of length 2, and that is each segment has length 1, right? So what we given two input sorted segments, a merge box knows that these two are sorted, so it can scan from the head towards the tail of each of these groups, knowing it's always looking at the next biggest thing from that segment. And by comparing those two, it can decide which one to move on into the output segment, which will be exactly the size of the pair of some of those things. So that's what a merge does, right? And every pass here, we have doubled the size of the span. So eventually we reach a size that encompasses the whole array, and then we know the whole thing is sorted. And the number of passes we're going to do is log n. So a couple of comments here. One is that that if you just look at this picture, there's actually looks like a huge opportunity for concurrency. Essentially, all these pink boxes can all go concurrently. You have to be a little bit careful about synchronization, where, for example, when this merge is trying to read from here, you shouldn't try to read it until this merge has put a value in there. But modulo that synchronization, essentially everything can go in concurrently, and that synchronization is actually exactly the IVAR synchronization that you might find in a Haskell. So you could write this with IVARs very easily. But of course, that will take a lot of resources. Conceptually, you're going to have log n copies of the array as you do that. So a cheaper alternative would be, given that these lower merges have to wait anyway for data to come in from here, is to just do one pass at a time, but try to do as many of these that you can in parallel at a time. So you go from A to B, doing as many of these merges in parallel, and when done, you go from B to A, doing as many of these merges in parallel, and so on and so forth. So that's roughly speaking the tactic we're going to use. So let's take a look at one single merge, right? So this picture basically shows you the names of various variables we're actually going to use in the code. Each merge we'll talk of as having a segment 0 and a segment 1. It has an index I0 by which it's scanning through this, and index I1 for which it's scanning through this segment. They both have the same span. They have limits. The I0 limit is I0 plus the I0 plus span. I1 limit should be this initial value plus this or the initial thing plus twice the span. I think I have some typos in these numbers here, but you get my point, which is that we have those, and then we have an index j, which says the next value that we're going to write out into this array. Okay, so now we're going to look at the code, and look at a couple of things in this code. So let's go to 4.0 merge source merge engine.bs. Let's first take a look at, let's get a few annoying things out of the way. We are going to be using the ARM Axie4 bus, and the ARM Axie4 bus has all kinds of fields in it, most of which we're not concerned with for this example. The only things we're going to be concerned with is when we do a read request, we want the address that on which we want to read. That's what this is, and that's all you need as far as a read is concerned. And what we would also similarly, when we want to do a write, we will have an address which is shown here as fabric data, and a data which is shown here as fabric data. And we're going to produce all the ARM fields needed for it. So in the main code, it'll be much simpler. We'll just see the address and data for reads and writes. So this is all boilerplate for creating Axie4 reads and requests. So let's skip all of that. Byte enables, burst sizes, all kinds of stuff in Axie4. Let's take a look at the interface. The key interface is are these two. First of all, these two, by which we tell it to do its merge work. The start interface takes these parameters, which is the those things. What is I0? Where does your span start? What is the length of your span? What are the base addresses of the two arrays of interest? And how many things are there in the array? What's the limit of the array? So that's the start. And done is bool, saying I'm done, I'm finished, I finished this merge step. And it will also have this initiator interface, which is basically an Axie4 master interface that through which it issues reads and writes to memory. And the init action thing that you see above is just an initialize, and we can ignore that for now. Okay, so the next thing I would like to do is maybe we should take a little bit a look at some code, and then there's a particular issue of deadlock that I would like to draw your attention to. So if you look at the engine, it has a merge interface. It initiates a transactor. Now, what's a transactor? So this actually relates to a question that somebody else asked earlier about Verilog names and interfacing with Verilog and so on, which is that in Verilog and in system Verilog, etc., unfortunately, people seem to people seem to define interfaces over and over and over again, even though they are using the same idioms. And what do I mean by that? Which is that you know, you're getting a value, you're putting a value, you're enqueuing something into a queue, you're dequeuing. These are sort of high-level idioms which, if you can capture in interface types, etc., you can just reuse them over and over again without having to redefine every time you define a module what is the interface is. And further, it's readable. As soon as you see that, you know what that interface is supposed to be looking at. Unfortunately, many Verilog and system Verilog interfaces, etc., are defined ad hoc from scratch for each module. So you take a long time just understanding what the interface is supposed to be doing. So what we do here is that we define these things called transactors, which is what is highlighted here. So this, let me just stretch this out for a moment. This is a transactor available to hide the details of all the specific signaling that the ARM Axie4 interface has, and says, just give me a high-level view of this thing as if there are queues. A queue into which I can put write requests, a queue into which I can put read requests, a queue from which I can get out read responses, and a queue from which I can get out read responses. So we solve that problem once, and then by using this transactor, we can we can simplify the code that we have to write. So that's what that is. Then these are all just registers that are holding all these interesting values. And let's ignore this credits, etc. for now, and start looking at the rules. Basically, and then these two FIFOs capture the values returned from memory. So I think at this point, it's worth looking at a picture before we start looking at code, which is the flow in the merge engine. What we're going to do is the following. We have two rules called rule request 0 and rule request 1. And what it's going to do is, this one is just going to generate all the addresses of interest for the segment that I'm scanning, right? And that's easy. I don't need any more information. I have the base address. I know how many elements there are. I can just churn out the addresses one after the other without looking at anything else. So that's what it does. It churns out the addresses and streams out read requests to memory. So it's pipelining read requests out to memory. Similarly, rule request 1 is churning out the addresses for its segment and streaming out read requests to memory. So those requests go out to memory. Doesn't matter what order they reach there, and they come back. When I say it doesn't matter what order, what I mean is the interleaving between the requests between request 0 and request 1 doesn't matter. In our code right now, it does matter that for a given set of requests, either from request 0 or from request, that they stay in order, but they can be interleaved in any order you like. So responses come back. And what we do with these responses is we look at the response and say, is it a read response that was generated by that rule? Or is it a read response that was generated by that rule? Depending on that, we take it out and we put it into these two FIFOs. Take it out of this FIFO. This rule now, therefore, sees those two segments that it is trying to merge. It's seeing the data coming at it as a stream in sorted order. So it just has to look at the head of these two FIFOs, decide which one is smaller, and write that out back to memory to the output array. So that's what this write request is. And the write request goes to memory. We get an acknowledgement. There's no data or anything. The acknowledgement is just saying, yes, okay, the write request happened, and comes back as a memory response. And that's one more selection we have to do here, which says, is the thing in the queue a write response? And if so, we come to this thing, which simply drains it. So you can see the data flow that is going on here. It's completely pipeline, and it's completely streaming data to memory and back. So as long as your memory interconnect and your memory and all can handle that kind of fire hose of reads and writes, this will generate it for you. So that's basically what the rule here does. So let's take a look at rule request 0. So that is this rule over here. As when I'm running and when I'm still within my span, that is, I still have data to look at. Let's ignore this for a second. This basically saying I'm allowed to send a read. Then what do? I compute my element address. It's the base address plus the index. And because our memory is byte addressed, we shift left by 3 to get a byte address for a 64-bit word. And we make a memory request, and we'll call that RDA. And this transactor says, please enqueue it. So these two lines produce an AXI4 read request and puts it out into the memory system. And then I just do my bookkeeping, which is I increment my number of requests that I've done. I'm going to decrement my credits and just print out a thing. So very simple. It's just directly expressing what I verbally said this rule does. And similarly, if you look at response 0, that's this rule here. What it's doing here is, first of all, it has to decide whether the response at the head of this queue is meant for me or not. Well, how do I know that? Well, what I'm doing, oops, I'm sorry, I clicked on this. When I generate this request, as shown here by the 0, I'm tagging a value on it, which is the value 0, saying I'm for segment 0. And if you look at rule request 1 here, which is the other request rule, you will see that it, in the same place, tags 1 instead. So this tag accompanies the request all the way to memory and back. So when you see a response coming back here, by looking at that tag, you can tell whether it was meant for segment 0 or for segment 1. And that's basically what this rule predicate says. When the first datum returning has tag value 0, it's for me. So I'm going to take it out of my input queue and put it into f data 0. So that's basically this rule moving it from here to here. And then there's similarly a rule request 1 and response 1. And if we look at rule merge, it's just, again, doing the obvious thing. It's sort of looking at the first element in this queue and the first element in this queue and deciding which one is smaller. And for the smaller one, it sends out the right request. Again, no, I don't think there's any need to go through the details of it, but it's kind of obvious what it's supposed to be doing.
So does that mean that we require the memory element to return results for a given request ID always in the same order as the requests came out?
Yes, correct. So, so what this means is that for requests with TID 0, the responses with TID 0 should come in the right order. And similarly, for requests with TID 1, the responses must come in the right order. They can be interleaved in any order, it doesn't matter. But for a particular TID, they should all be in the same order. That can actually be generalized. But it involves creating a little more hardware, because if responses come out of order here, you have to, first of all, you have to have a tag on it to say what order they should be in. And then based on the tag, you have to have some circuitry that puts it back into the right order. I've taken a simplified view in this example here. The AXI4 interconnect is able to handle many of these things, such as out of order responses and so on. So one issue I would like to bring up here, which is what all these things about credits is concerned, is a question of deadlock. Oh, I keep mistakenly clicking on these pictures, which opens out something else. Okay, it's a question of deadlock. So here's the scenario that you have to be a little careful of, which is, just imagine that f data 0 got filled up because you were not, because they were large values, so you were not taking them out. Smaller values were coming in f data 1. So f data 0 got filled up. And then imagine that f data 1 became empty. Okay, now imagine that in this queue, you have a response for f data 0 in front, and behind it is the next one for f data 1. Now you're stuck, because the only thing you can look at in a queue is the thing at the head of the queue, which is for f data 0. So there's no way to bring that f data 1 gadget datum out into this queue. So this is classical so-called head of line blocking, right? It's standard textbook concurrency deadlock kinds of issues. And the solution is also completely textbook standard, which is that what we do is we keep a counter, which we call the credit counter, which is what this thing is. It's basically, think of it as a register. And what that register is doing is it's saying that I will limit how many read requests I'm allowed to send out from each of these rules. And I will make sure I have enough buffering here to hold all the responses that might come back, so that there is nothing so that nothing needs to be stuck in any of the pipelines along the way out here. So you, let's say our credit counter value is, let's say 16. You're allowing 16 reads in flight. So you initialize the credit counters to 16, and every time you send a read request here, you decrement the credit, and you never send out a request if your credit goes down to 0. So all of that is expressed in those rule conditions that I showed you out here. And so you essentially stop sending requests after you've sent out 16, and because you have enough buffering here, you will never be in the situation where it's sitting at the head of this queue. And then what you do is every time you consume this value here, you increment that counter, saying, okay, you can send one more because I've just consumed one. So you replenish the credit during this. So some of the code you see here is just that kind of a credit management for credit-based flow control on this pipeline. So this is a standard thing you'll encounter in many kinds of pipelines, which is that when you do pipelining like this, and you have pipelines that branch and merge together, as is happening in this example, you can get into this kind of deadlock, head of line blocking situations, etc. And you have to be very careful about how you do this. There are other solutions like prioritized queues and all that, but all those standard textbook solutions do apply. You just have to express them in suitable hardware structures here that do exactly those things.
Question. So if
Yes.
I look at the code, I notice that the registers holding these credits seem to be not just simple registers, like they're made with mux, c, reg, u.
Correct. Okay, good. So let me just paraphrase the question. The credits register here, for ordinary registers, I'm using these things like mcreg u for uninitialized, or some mcreg with some initial value, etc. Now, for these credit registers, I'm using something called mcreg creg u instead of mcreg u. And why is that? Okay, so let's just discuss that for just a second. So when rule merge consumes an element from here, it wants to increment the credit that will allow rule request 0 to send its next request. And rule request 0 itself, whenever it sends a request, decrements that register, right? So both rules are reading and writing a register. One is incrementing, one is decrementing. Now that's a tough thing to do in hardware, right? Because a register gets its value on one clock, and its value holds until the next clock. If we wanted to run those two rules together in the same clock, now first of all, you can leave it as an ordinary register. We could just substitute there mcreg u, and it would all work. All that would mean is that those rules would not be able to fire in the same clock, which would just mean that when you run out of credits, you're going to have to wait until this guy replenishes a credit, and then on the next clock you could send a read. If you were able to do this increment and decrement in the same clock, then on the same clock that you do the increment from here, this guy might be able to then send and also decrement, so keeping the register value effectively at a constant value. So it's really about being able to squeeze those two operations into a single clock that this concern even arises. Now, in this particular example, it may not matter much because the latency involved of a read and a write involves, getting into this queue, getting out onto the bus, going through the bus, going to memory handling it, memory sending it back, coming back through the bus into this, etc. It could be many cycles for a request to eventually show up here. So, delaying a load by one cycle may not be that critical, but there may be situations where it's absolutely critical that you need to put those two things together. So that's what a creg is, and it's called a concurrent register, and that's why it has this name creg. And you can think of it as an array of registers, which is why you have this type for its interface. It's not just a reg U8, it's an array of registers. And the key thing about cregs is that in this array is that if you think of the indexes of this, and if you think of these registers having 2 ports, which is what this number here 2 is, so port 0 and port 1, what it says is that if you do a write into port 0, you can actually do a read from port 1 of exactly the value that you just wrote within the same clock. And this allows you to do both those increments, the increment and decrement, sorry, within exactly the same clock. So we've actually verbally gone through the section that was to follow on this, but that's just as well because I don't think we're going to have time to really go through that. But this has brought up a very useful and important point. So just to summarize again, you could functionally get everything running just with registers. And this is true not only in this example, in many, many examples. You just think of rules, you think of registers, you write rules. And usually for reasoning about correctness, you are just relying on atomicity of rules. That's it. That using atomicity on rules and sort of induction on state, you know, I'm in a proper state now, I'm going to execute this rule. It's atomic, so I know exactly what state change it performs. Therefore, I know the post state is correct. And you just repeat that process over and over again to overall show that correctness of a design. And so you can think along those times. So these concerns about C-regs, etc., come often as the next level concern of performance, which is, okay, it's functionally correct, but my design doesn't execute in as few clocks as I want it to execute. What can I do to fix it? And this is exactly the kind of tweak you might do. You might substitute an ordinary register with a concurrent register, which says, oh, okay, this will allow BSC to now schedule those rules together in a single clock, thereby improving my overall performance. Okay, so let me see where we are. We're almost at 3 hours. And by the way, I want to just say something, which is that I was originally told the tutorial is 3 hours, and then I was told that all tutorials are 3.5 hours. I'm not sure what message came to you about this, but if you can extend beyond, we're 4 minutes away from the 3 hour point, but if you can extend a few minutes longer, we'll just close out and we'll wrap up all of these things, and we can perhaps spend more time on questions, answers, and so on. Okay, so let's take a look at what hardware we're creating. This is a pictorial view of our merge engine. It's the outer level thing is this Axie4 Accel. It's the thing that has these 4 registers that we configure with the address of vector A, address of vector B, and the size of vectors. And once we get, and in register 0 is what we call our control and status register. When you write a 1 into that, when the CPU writes a 1 into that, it will say, go, start your work. And then some rule here will call, there are a bunch of rules here that will repeatedly invoke the merge engine, calling its start method to do a merge. And when the merge engine is done, it'll invoke merge engine again, and so on and so forth, until it has done a single pass from one array to the next. And then it'll repeat that again, and then it'll repeat that again, each time doubling the span until the span has reached the size of the array. So if you look at, looking at this module itself, you see the read responses. We saw this is the merge rule that we briefly looked at, and then we have a drain write responses. So let's just a few comments about the drain. Why am I draining write responses, and why do I bother, since I'm just throwing it away? 2 answers to this question. One is that in many algorithms, you need to perform computation A before computation B. And how do you know that A has finished? If you just launch A and you don't know when A is finished, how do you know when to launch B? Particularly if the last things that A does is a bunch of writes. Those writes may still be in flight on the way to memory. And if you launch computation B too early, it might go and read those things too early. So in some sense, the round trip on writes allows you to better handle that kind of synchronization. That is, you can sequence the reads, be guaranteed that the reads that follow are always after these writes. So that's one question, one issue. The other issue is, of course, that hardware systems can have errors in them. So, and oh, there we go again. I only clicked on this. If you come back to this original picture, you know, when you send a read request to memory and the response comes back, or a write request to memory and the response comes back, you might get an error. It could be an alignment error, it could be an electrical error, it could be an address out of range error, all kinds of things can happen. So it's generally useful to look for the response and check for error responses. Now in my code, I've been lazy and I'm just discarding the response without actually looking at the error. But basically, that's basically what's happening over here. And that's it for the merge engine. And now if we look at the merge sort example itself, the top level box that is in this picture here on the right. First of all, let's look at its interface. Sorry. So the interface for this box is this, which is defined in the Flute repository because it's a generic interface for accelerators. It's not specific to merge sort or anything like that. And we can take a look at it. Actually, I think I have the interface in the document here. It's happens to be written in BSV, but if you squint at it, you can read BH in it instead. So here's the interface for the Excel interface, right? So there's an initializer, which is fine. Let's forget about that. And this is all there is to it. There's one so-called Axie4 slave interface by which it gets configured by the CPU, and there's one Axie4 master interface. That's through which it does its reads and writes. So those are basically the two interfaces. All these parameters are Axie4 parameters. How wide is the address bus? How wide is the data bus? Things like that. And the other thing to see is that here's the BH version of it if we had written in BH. And you can see that modulo rearranging some words and stuff. It's really exactly the same interface. So here we have the init interface over here. This is its first argument. Here's its first argument, second argument, and then the final result, which is shown here. So there's these types are written in system Verilog style, which is basically C style, where the function result is written, type is written before the function name rather than at the end. But modulo that, it's really the same thing. So in fact, with a little bit of practice, you don't even see the difference. They look the same to you. Okay, so that's what the interface is. And then the rules itself, there's what you will see is there's one big rule for handling reads from the CPU. That is handle, configure, read requests. And all it's doing is it's taking the address and from the base and taking it away from the 8-byte address to a 64-bit word address to get an index into which control status register we're looking at. And then, basically, finally, what it's doing is it's producing in this Axie4 read data response. Here's the data. It's reading the CSR corresponding to that interest. In some of my notation here, you'll see I'm doing an explicit read, which I said could be with syntactic sugar implicit. I think there are some weaknesses in our compiler where this doesn't always happen. And so sometimes you have to, if you use the method notation, it works fine, but it complains somehow if you don't. Especially when you do these things like vectors and selecting a register from a vector of registers and so on. But this is basically a read of this index register in that vector of registers. So that's read. Similarly, you see a write configure register, and down here you see that I write the data that came in on the bus into the vector of CSRs. And then you see a bunch of rules which are doing, they're very boring rules. They're encoding in rules. A state machine, again, I think I have a pseudocode version of it. you know, when you get the go command, you have an outer level loop at L1 where you keep doubling the span size until it's large enough, doing a pass. In each pass, you initialize the pass with the index starting at 0. And then as long as the index size is 0, do one merge and so on. And then wait for all merges to complete, and you're done. So how are we going to run this? So just a few words about this. You can look at the details again separately on your own. But if you look at the make file here, first of all, you will see here a definition for the flute repository. So if you just git clone the flute repository and make this point to your flute repository, that part is done. Then you see a bunch of things that are really all about flute. Flute is a RISC-V CPU. You can choose whether it's a 32-bit CPU or a 64-bit CPU, whether it supports atomic instructions or not, whether it supports compressed instructions, integer instructions, the hardware multiply, divide, user mode only, or virtual memory mode, how many privilege levels, machine mode, user mode. You know, you can define all of these kinds of things here, and some details out here. But these are all configuring the RISC-V to be a 64-bit CPU. And then what we're doing is then we just do a make, and this will go and pull everything you need for this to produce the executable. And then when you finally finish that, we can do a run of that. So let's in fact build that. This will take a little bit of time, but maybe a minute or so. And so this is a full 64-bit CPU. It's actually capable of booting Linux and FreeBSD and FreeRTOS. It's being used for all of these things. It's got the sort of full functionality of RISC-V. We're not using it with that full functionality. We're just doing a bare metal RISC-V with no operating system or anything like that. And we're just going to use it in that bare metal mode. So this is just building all of this. It's building a UART. It's building a boot ROM. It's building the interconnect. Here we are doing UARTs, caches, virtual MMUs, the whole works. Everything is being compiled here. Essentially, all of Flute is written in BSV, but like we saw in that interface example, it's quite easy to read from if you know BH, and vice versa. Maybe not vice versa. I think people who know BSV have a hard time reading BH, but people who know BH have an easy time reading BSV. They probably gag a little bit, but that's okay. Okay, so now let's just talk a little bit about software for this. So what we're doing is we're building it, but how are we going to run it? So what we're going to do is, so going back to our earlier picture of the overall system, here, we're going to be running a piece of code on Flute. This is RISC-V machine code. So where is that program? That program, of course, sits in memory. You're going to do instruction fetches across this boundary to fetch instructions. You're going to execute it in that pipeline. It's going to do loads and stores, which do this, etc. So we need to start with a RISC-V program here. How do we get that program? So I've pre-built some programs for you, but I've also explained how it's done in case you want to do it later on your own. So we're going to do two programs. The first one actually has nothing to do with merge sort, just for demonstration. Since it closes the circle, we started with a hello world example in hardware. Now we're going to do a hello world example in software running on hardware that we've generated from the kind of hardware which we explained using hello world hardware. So we run it through standard GCC, except targeting RISC-V. So either it's a cross compiler, or if you're running on a RISC-V machine, it's a compiler, regular GCC. And we produce a standard ELF executable, binary ELF executable. Now, usually when you have an ELF executable and you run it on your laptop, it's the operating system that's taking the ELF and unpacking the ELF file and initializing your instruction memory before your process starts. We don't have any such OS. We don't have a loader, etc. So we're going to do those steps a little manually. There's a program called elf to hex, which takes that elf file, unpacks it, and produces a file called mem.hex, which is basically a ASCII file giving a hexadecimal listing of what should be the memory contents for this. And we call that file mem2hex, and we provided all of these pieces for you already. So once we've done this, if we say make run hello, here you see your little hello world coming out here. And what is this program hello world? Well, if we go to resources, C programs, hello.c, it's your standard one-line printf hello world program. We've had a few things added to it. This thing allows us to do some cycle count timing, although I'm not really using that in this program. And this thing allows it to decide whether the test has passed or not. You're seeing some extra stuff. Just ignore all that. It's basically the standard C hello world. We've run it through that GCC thing. We produced an ELF file. We've run it through ELF to hex to produce a memhex file. And when we run this here, this program here, what we're doing is we're copying the pre-generated memhex file here. We also copy a symbol table by which the simulator knows certain things about where to start the program and things like that. And then we run it. And what you're seeing here is first of all, the top level SOC giving a banner. A little later, you're seeing flute giving a banner out here. A little announcement from the caches about the associativity and sizes, etc. And then it starts running. And during the run, how does this hello world come out? Well, as you do the run, when that printf calls certain libraries that are part of the GCC build here, that converts that printf into store instructions to the UART. So it reaches the UART, and our UART model just takes whatever byte you write to it and prints it out on the screen. So that's why you see hello world sitting out here. And similarly, if we do the other test, merge sort, it's going to do the same thing with the merge sort memhex. And in fact, let's take a look at that code for a second while it's running. And if we look at main, you will see that it does a run with not accelerated and a run with accelerated. And if we look at the run code, whoops, sorry. If you look at the run code, what you will see is it calls merge sort, this function, or it calls merge sort accelerated with exactly the same arguments, PA, PB, and N. And it has some boilerplate around it to count cycles, read cycle, write cycle, etc., to measure time. And in the end, it prints out the cycle count. And if you look at those functions in turn, if you look at merge sort, it's just a software implementation of merge sort, right? So when you call merge sort with PA, PB, and N, this is the outer level loop that's doubling the size of the span every time around. Every time it calls merge engine, and then merge engine just does the merge, just like we described. That's the software version of it. And if you look at the merge sort accelerated version, what you see here is that we just write out the address and the size to the accelerator. And then we say go by writing to the CSR register. And then we are sitting in essentially an idle loop here. We could be doing some other work instead, but we're sitting in an idle loop here, reading the accelerator base register 0 until the status goes back to 0, and then we're done. You also see a few things here, which is typically what you will see when you work with accelerators and so on, which is that before this call was done, the software was producing the input array. So that may still be sitting in the CPU caches. And so what this fence says is make sure that those things have been pushed out to memory so that when the accelerator starts reading it, it actually sees the latest values. And conversely, this fence is doing the opposite. It's saying the accelerator has updated memory, and I may have old values in my cache. I should make sure I reload those values so that I get the values that were created by the accelerator. And these fence instructions are expensive because they're clearing caches and so on. There's a whole, that could be a whole topic in itself, how to deal with those kinds of synchronizations. But briefly, what you see here is we've run this merge sort on an array of 3,000 words, and it took this many cycles, 1,932 cycles. And then here we are running the accelerated sort. These two things, by the way, are just printfs that are coming out of those fence operations. In both cases, we are verifying that the output array is indeed sorted, and it took 321K. So this is about a 6x speed up from, but which is not that dramatic. There are accelerators where you can get 1,000-fold or 1,000,000-fold speed up. So this is not that big, but maybe merge sort not such a good example for that because it's not doing any computation other than reading and writing from memory. So if you're limited by memory bandwidth, whether you write a program or a piece of hardware to do it, you might not get much better. But we still got a little bit of speed up on this. So, so that's basically it as far as the tutorial is concerned. Just to summarize what we did, what I've tried to show you is that we have a language that essentially uses exactly Haskell syntax and the type system of Haskell, namely type classes, monadic constructs, monadic types, and things like that. Except what we're describing is not what will run on stacks and heaps, but what we're describing is hardware. And it's just describing structure of hardware expressed with some constraints because of rules, and rules having atomic semantics. And what we do when we run it through our compilers, we produce classical synthesizable synchronous Verilog hardware that implements those atomic semantics that is specified in the structure that was specified in the hardware. And we produce that hardware, and then that Verilog, it's, when I say it's classical synthesizable Verilog, what I mean is this can feed straight into standard Verilog tools. Now, often when people design in Verilog, they have to go through some additional jumps to make sure that they have stuck to the so-called synthesizable subset of Verilog, VHDL, or system Verilog, so that they don't have these surprises between simulation and synthesis and so on. We only produce that synthesizable subset of Verilog, so it's no further checking needs to be done. There is a whole array of linting tools one typically uses on standard Verilog to make sure you're within the synthesizable subject. There's no need for that here. You go straight through into standard Verilog tools, and we produce the Verilog. And so I've finessed the question here about how we might send it through the remaining flow, but that would be a whole tutorial in itself. So we have also brushed against issues of concurrency. We start with this sort of very sacrosanct idea of atomicity of rules, and then we describe in our discussions of concurrent registers and so on how there are nuances you have to be careful about how multiple rules can be packed into individual clocks so that one can meet performance goals and so on. But modulo those nuances, you can essentially design anything you like with BSV. And because you're designing microarchitectures, I literally mean anything you like. In fact, there was an earlier question also about, are there certain kinds of designs that work well and don't work well with BSV? And my answer was, no, I don't think there are any design. And the reason for that statement is that because you are describing microarchitecture in a similar way to how you would do it Verilog or VHDL. Anything you could have said with those languages, you can also say in this language, except you have much more powerful abstraction tools and correctness tools in terms of type checking that automatically come with this. And in contrast, if you look at what I said, my remarks that I made earlier about so-called high-level synthesis, where you write in C or C++ and have a tool generate the hardware for you, because it's automatic parallelization, they work well with certain kinds of programs, loops with rectangular arrays, and not well with other programs. But that's because you're not describing microarchitecture with that approach. Here, you are describing microarchitecture, so you can be just as expressive as you were with Verilog or VHDL within the domain of clock digital circuits. So there are lots of topics that we haven't had time for, which I'll just sort of show you on the table of contents here, if you can go through at your own pace at some point. But you'll see that there's a section on how you deal with multiple clocks and clock domains, reset domains, etc. There's a whole section that goes into a lot of detail on these concurrent registers that I have sketched over in the description that I gave. And then more details on all of the examples out here. So I think with that, I'm ready to stop the sharing and come back to my picture out here. And we have about 5 minutes, 10 minutes left scheduled, but I'm not in any hurry to leave or anything. So if there's any questions or discussions you would like to have, now's the time for it. Remember that you're all or mostly muted, so if you want to speak, and you might want to unmute yourself.
So what does bare bones I/O look like in BSC? So suppose that I have a single bit of input from a push button and a single bit of output to an LED. How does that work? Because we've only seen like these action calls. And
yes. Okay. So so this relates to an earlier question that I had, earlier discussion that I had alluded to. If you think of any method call, method implementation in the Verilog that we have, every argument for a method becomes an input wire into the module. And every result from the method, whether it's a value method or an action value method, becomes an output, I shouldn't say wire, a bus. It could, because if it's a int 32 type, it's 32 wires coming out. It's a bus of 32 wires, okay? So there are buses for each argument and buses for each input. In addition, the default thing which you saw was that every method has one output wire, which is called the ready wire, which tells you whether the method is eligible to be invoked or not. And for action and action value methods, there's one additional wire going in called the enable wire, by which the environment says, now is the time to do your action. Now, that is the general case. You can pare it down to a single wire going in or a single wire going out, right? So if you take a value method that is always ready and that has a Boolean output, but because it's a value method and it's a Boolean value, the output bus is a single wire. Because it's always ready, that wire doesn't exist. In other words, there's these annotations that you can give in the interface that says always ready, always enabled, etc., gets rid of any of those control wires if they're not needed. So a single Boolean method that is always ready will be a single output wire. And conversely, if you think of an action method that has no arguments and no results, is always ready, it has a single enable wire coming in. So whenever the enable wire happens, you do whatever you want inside. So you can always reduce the general mechanisms that we've shown here into mechanisms that mimic what you do in Verilog or in system Verilog. What we find is we very rarely think in those terms, except at the edges of our designs where we have to interface with other designs that may have been written in Verilog and system Verilog. And what I would recommend to you is, if I can just continue my sharing for a second. Let me just continue my sharing. I just want to show you where something is so that you can. So in this merge sort example, we were looking at flute. So if I go to that directory, so this is the flute. This is the GitHub flute repository, which includes the WinSock SOC. And in this directory, if you go to source, test bench, fabrics, axi4, I think I have mentioned this in the document also. So if you're not copying it down, that's fine. You'll be able to find it in the document. What you will see here is a bunch of files. Yeah, and the particular one you might want to look at is this one, which is called axi4 types. Because here is an example of something where we are writing something in BSV, and it is intended to connect to other gadgets that somebody else may have designed that claims to be an axi4 master or a slave. So their design is going to be in Verilog or system Verilog, and it's going to have exactly the wires specified by ARM for an axi master or a slave interface. And it's going to follow exactly the protocol of the so-called ready and valid signals going in opposite directions from that ARM is designed as the way to exchange data on an axi4 channel. So this file, if you look at it carefully, you will see how all of this is done. How do we get the names of interfaces to match what the Verilog expects? How do we just deal with wires and manage protocols explicitly rather than letting BSV manage protocols of interaction, etc.? All of that is embodied in examples over here. So this is a more complex example, but the same principles apply to the sort of simpler question you asked, which is what do I do if I have a single wire coming in from a button or a single wire going out that's going to an LED? You're at the edges out here, and like I said, this is how you would, these are the principles you would use to achieve that. Any other questions or comments or anything people would like to add? Hi.
Hello. Hi. I'm curious about the general verification story for Bluespec. You know, in general, in industrial settings, you write SVA properties, and then you can prove them using off-the-shelf tools. But what is the story with Bluespec on that? Okay,
so good question. I think a couple of points here, which is we do not have major formal tools yet. They're in progress, but we don't have them yet. And so let me sort of elaborate a little bit on that. First level is, I want to say that there is a baseline here that's already a big step forward, in my opinion, right? And the baseline is simply having to do with, first of all, strong types and strong type checking. Very strong type. Basically, it's Haskell level types and type checking. Many things that people have as bugs in Verilog and system Verilog are simply caught as type errors in BSV. And you know, there's a standard sort of aphorism. Some people may call it a fable. In Haskell, you get your types right and it just works. You often see that kind of a behavior in BSV as well. You know, you get your types right and it just works. Because the other thing, in addition to strong type checking, is that the atomicity of rules is the major value add in Bluespec on top of the, you know, these are the two major things. On one side, Haskell level expressivity to describe structure, and then atomicity of rules and compositional rules. Because as you saw, a rule plus a method it calls plus a method that may call collectively transitively form a complex rule, a large complex rule. So we have composed a rule out of pieces, which are the methods that it calls, and the whole thing has atomic semantics. And this is a very, very useful property by which to reason about correctness of codes and so on. So again, lots of errors that might happen due to race conditions in Verilog, VHDL, etc., are just defined away by the fact that it's atomicity. So, but this is a baseline. That doesn't mean you can't have bugs, of course, in a BSV program. You can have all kinds of bugs because at the next level of abstraction, higher concepts of atomicity, etc., are not going to be captured by the primitives that we give for all of these things. So at that level, we do not at the moment have any usable tools per se. I'll just say a few things here. One is that there is still not going into full formal verification. There is a version of Quick Check available for Bluespec, which was developed at University of Cambridge in Simon Moore's group at University of Cambridge. It's called Blue Check, and actually if you search for it on GitHub, you'll find it. And it's basically the fact that in BSV, because we have the full Haskell expressivity of monads and all those and things like that, it is Blue Check expressed in BSV. It does everything that Blue Check does in terms of automatically doing stimulus, automatically recording stimulus, doing shrinking to find smallest counterexamples, all that kind of thing. So you can play those kinds of games in BSV as well. And that's available from University of Cambridge's website. In terms of more formal verification using proofs and those kinds of things, that is still in the research phase. I think the maximum work that is happening on that front is in Adam Schlipala's group at MIT and Professor Arvind, who's, by the way, with us on this call. Hi, Arvind. So the idea there is what they do is they are essentially building a system called KAMI, K-A-M-I, which maps BSV exactly, or BH exactly into Coq, and then they use the machinery of Coq to be able to reason about correctness on these programs. And correctness can mean the targets for correctness is many things. One is simply, here's my design. I think it does the following. Does it do it? You can also have performance criteria. I think it does it in so many clocks. Does it do it? That's another kind of correctness. But there's another kind of very interesting kind of thing, which is that here's my merge sort. I used ordinary registers for the credit counter. I'm substituting concurrent registers for it to improve performance. So I did a transformation on the code. Is it still correct? So those kinds of questions are all within the purview of the kinds of things that the MIT group is doing. But like I said, that's not usable yet in any kind of production use.
Right. Yeah. As a follow-up, I can imagine from a purely practical perspective.
Sorry?
So I'm thinking it would be almost, can you hear me?
I can hear you, but it's
I'm thinking like you won't be able to. Oh, okay, I'm sorry. I'll try to speak quickly. I can imagine you cannot, turn an entire design, a huge design, all to Bluespec in one go. But I might be able to say, hey, I'm going to write this module here in Bluespec and then merge it with everything else that other people are doing. In that scenario, have you had any experiences with that? And how do you verify now that this Bluespec module works correctly in the presence of all the other artifacts that you get from other sources?
So again, we don't have too much tool-wise experience on that, but let me give you a property that actually helps a lot on this, which is the compositionality that you get from the way Bluespec is defined, which is that when I look at a module and its rules and the methods that it calls in submodules, I only need certain abstract information about the submodules. Specifically, I have the interface type definition, of course, what its methods are also, but I also can if you give me as a declaration the scheduling information about those methods, that is what rules conflict, what methods conflict, or if they don't conflict, what ordering must they go on. That is enough for me to reason about correctness about this module that's using that module. I don't need to get into the details of that module. So it is possible to build up a reasoning fabric, if I can use that term, incrementally by proving something about a module, abstracting some property about its interface, and then just using that abstraction at the next level up. So you're not always talking about large things, you can do that incrementally. Now, I'm saying this, we do this sort of informally a lot, and I think the people at MIT are formalizing this in their tool, but it's still not available in any sense as a usable tool or anything.
If Nikhil, may I say one thing?
Yeah, please. This is Professor Arvind, by the way, from MIT. Please go ahead.
I think we have a lot more experience importing things written in Verilog in our Bluespec designs. So if there is some module that already exists and you want to import it, we can do that as long as interface definitions are preserved and so on, and we can even verify formally some properties of them. Going in the other direction is a bit harder, because when the total design is in Verilog, I mean, I'm not sure I understand all the nuances of it. And if you replace some module in that with Bluespec, it can work, but we just haven't spent enough time on that.
Yeah, thanks. I think the other point to make is that it's still early, despite Bluespec being 20 years old, it's still early in this game of formal verification. But I think it's the best platform on which to try this because of the atomic transactions and the Haskell type checking and strong type checking and things like that, which is, if I were to look at the range of languages out there and say, if I want to do something in formal verification, where do I start? This might be the best platform on which to start doing that work. So if those of you are interested in formal verification, I hope you're inspired to think about that and do something on that.
And people may want to look at the PLDI 2020 paper on Koika, which is also from Adam's group, done by Clement and Thomas. I think that says a lot about scheduling and how to control scheduling and prove things about cycle counts in a program.
Can I make a comment?
Yeah, hi, Larry.
Hi.
Go ahead.
So, so replacing a Verilog module with a Bluespec module, I assume that if you're doing that, you already have a testing framework for your Verilog stuff. So you can just plug in one for the other and run your usual tests and run all your sort of tools like formality or whatever on the generated Verilog. So, I mean, we've done things like that in the project I was on before. And I wouldn't say that Bluespec is any more difficult to do than doing a rewrite in Verilog or something else.
That's a good point.
Okay.
Yeah, thanks. I'm just worried about the practical considerations, but maybe that's beyond the scope of the current argument.
I can make one more comment, since we have designed a fairly large chip using Bluespec, and it was a great experience. I mean, people who designed chips before said that they've never seen a design that had so few bugs when you come to the total integration of the system and trying it out on sort of end-to-end verification.
All right, so thank you all, and I encourage you to go look at the code in a lot more detail at some other time when you have time. And in particular, like I said, in addition to the examples in this tutorial itself, I've given you a pointer to Flute, but if you look at sibling repositories to Flute, you will also find another processor called Piccolo, which is a smaller processor than Flute. It's a 3-stage pipeline. You'll find a larger processor called Tuba, and you can now see why this SoC is called WindSock, because they're all wind instruments. And the Tuba larger design is actually the CPU part of it, which is a major part of it, comes from MIT, and it's a full-blown RISC-V superscalar, out of order, speculative this, speculative that, all kinds of branch prediction, the works. It has everything in it. Cache coherence. It has all that stuff in Tuba. And it's all parameterized. So it's not as if it's one particular data point in how wide is the superscalarity, how big is the cache, which particular protocol are we running on the cache, etc. It's highly parameterized. So that's the other power that you get out of Bluespec. You can parameterize it in very powerful ways to get a big family of designs from a single piece of source code. So I would encourage you, if you get a chance, to go take a look at those. And you know, if you have any questions or anything later on, feel free to ask me, send me email or something like that. And you know, other experts here you see on the call on Bluespec, particularly Leonard, of course, and Arvind here. I don't know if there's any other Bluespec experts per se. A lot of people here know about it, but you can ask us all questions about anything to do with the language or the semantics or the tools or anything. All right. Okay. If there are no further questions, we shall call this session to a close and say bye-bye. Thank you.
Bye-bye.
Very much.
Thank you very much.
Thank you.
Thank you. That's wonderful.